I'm sure by now most of you have heard of the multiverse idea. The idea involving not just one universe where we live, but potentially a lot of other universes that we're just not able to see for one reason or another. And although the concept of the multiverse for the most part became famous because of various science fiction movies, including of course superhero movies, unfortunately when it comes to actual science, at the moment there is really no evidence for anything. And more importantly, the idea of the multiverse technically describes completely different phenomena. And so, hello wonderful person, this is Anton. In this video I wanted to discuss one of the recent announcements about a potential experiment that's actually going to try to find out if the multiverse exists, but also briefly discuss certain misconceptions about the multiverse and focus on what evidence we might already have today. But first of all, let's get started with the misconceptions and with the basic definitions. So, multiverse. Not to be confused with the parallel universe, not to be confused with other types of multiverses. Because by itself, the title multiverse does not explain what theory it actually connects to. And the multiverse that we usually see in various science fiction movies is usually based on quantum physics. It's better well known by the term many worlds. And here it suggests that every time something quantum happens to a typical particle, it tends to collapse into various probabilities, creating completely different outcomes. Or I guess in other words, when we measure something, and when the quantum world becomes real world, at least in theory, it basically creates different versions of different worlds that we're just not able to observe. And by itself, this is an interesting interpretation of quantum effects and quantum physics, but once again, there is no evidence, no proof. And though it does supposedly create the multiverse as well, here proving this would be extremely challenging, because there's absolutely no way we can ever detect these parallel universes using modern physics, using modern technology. But then there's also the idea of inflationary multiverse, and this is a little bit different. It's something that was originally proposed back in the 80s by Andre Lind and Alan Guth, and all of this was a result of the inflationary theory, which was proposed by several scientists. Now, in short, the cosmological idea of inflation in essence tries to explain why the entire universe appears kind of smooth and kind of flat, as if it suddenly expanded extremely quickly not so long after it was formed 13.8 billion years ago. It's not actually entirely clear why it happened, but it's the only way to make sense of current observations of the oldest light in the universe, the cosmic microwave background. Today it's believed that we might get some answers about this once there are even older discoveries from, for example, gravitational waves, but at the moment this is all we have. And so we know that in a tiny fraction of a second, the universe potentially expanded, increasing in size by a dramatic amount. But when the scientists were exploring this idea, they realized that, well, first of all, why exactly did it stop? As a matter of fact, maybe it only stopped in our universe, with the rest of the area still inflating even now. And more importantly, it also suggested that there could be other similar areas where the inflation suddenly stopped, forming separate individual bubbles that in some sense we refer to as the universe. And so the idea of this inflationary multiverse, that's what a lot of modern physicists are trying to learn about, trying to prove or disprove, and essentially are trying to understand in order to learn more about the timeline of the universe we live in. But we only can obviously do that if we discover any one of these other bubbles, other universes. And in this case, the theoretical assumption is that this inflationary space would make these bubbles separate extremely quickly, with none of them potentially interacting with one another. And so there would not be really any effects of one of these universes on the other. Except that maybe in some cases, some of these tiny bubbles could be formed close enough together where they might have a brief chance to interact before the inflationary process separates them once again. And so if we assume that some bubbles form much closer, it might become possible to find certain types of evidence. Okay, sounds cool, but maybe so far really far-fetched. How can we possibly find evidence in any of this? Well, once again we have to look at that ancient light. Today it's believed that a lot of the afterglow inside the cosmic microwave background has the potential to show us what happened even before the universe became too big, as it was developing right after the Big Bang. And several studies from approximately a decade ago established that by looking at the CMB, we can potentially find certain signs of these previous universes interacting with one another. So basically a kind of a bubble collision, bubble interaction, and some sort of a bubble warping. But what exactly would it look like? They might just look like typical circular features that should not be there. Basically sort of like craters present inside the cosmic microwave background, but craters that would be otherwise unexplainable and would not really make sense unless something else extremely massive interacted with the universe. And in the last few years, there have been certain propositions, with some of the studies potentially discovering up to 4 of these. Today these are referred to as the Hawking points, named after the iconic Stephen Hawking, and many scientists, such as for example Roger Penrose, do believe that these are maybe signs of interactions with other universes, evidence for the multiverse. But many other studies disagree, and there's actually quite a lot of counter-evidence providing a lot more explanations that you can learn more about in some of the links in the description. Basically, it's either a result of human bias, or in some cases a result of very large gravitational clusters. Anyway, nobody actually knows right now what caused this, so definitely not enough proof just yet. But there might be experimental way to prove this. And specifically, there's maybe a way to design an experiment right here on planet Earth in order to then create a kind of a tiny multiverse just to observe the interactions with these hypothetical bubbles in order to then try to match it to physical observations from the cosmic microwave background. In other words, scientists have now started proposing creating a kind of a tiny multiverse right here on planet Earth just to then compare it to the observations from the oldest light in the universe. And though it might once again sound kind of far-fetched, the actual experiments turn out to be somewhat intriguing, and they're based on physics that do make sense. And it once again takes us to the world of quantum physics, the physical laws that take over when things, for example, get extremely cold. And we know that when things turn quantum, things start to behave very differently. For example, there's the idea of quantum tunneling. Something jumps from one area to another without really doing anything in between. Okay, so this might get a little bit complicated, but bear with me. So the scientists here propose the following. First, because of the inflation in this case, they believe that the inflation cannot really produce true vacuum. But inside of this inflationary stuff, because of quantum fluctuations, the cosmos itself can tunnel through into a much lower energy state, producing a kind of a true vacuum, or in other words, forming a new universe. In other words, here the suggestion is that all of these bubbles form inside of this inflationary cosmos as a result of a kind of a quantum fluctuation that produces miniature vacuum bubbles. And sometimes these bubbles can form really closely and interact with one another. Now the actual math and physics behind this seem to make sense, but it's obviously a concept that's kind of difficult to understand. And though the math in this case might be sound, once again, up until recently, there was just no evidence or no way to provide evidence for any of this. It's a cool thought experiment, but that's about it. And that's until relatively recently, when several scientists whose paper you can find in the description published an equation that seems to connect this to the unusual type of matter we discussed many times previously, Bose-Einstein condensate. The phenomenon that happens to a lot of different atoms when they reach extremely low pressure, but most importantly, very cold temperatures, usually close to absolute zero. And that's essentially when a lot of these atoms start to slowly behave more and more like particles, and eventually all of their waves sort of merge into one megawave, creating one wave-like structure. This is what we refer to as the Bose-Einstein condensate, and it basically creates a formation where different atoms act as a single object, a single quantum collective. This paper, though, was able to show that many of these Bose-Einstein condensates potentially form similar vacuum bubbles that can actually help us learn about the multiple universes as well. So basically, they mathematically connected a microscopic world involving atoms assuming a quantum state to a macroscopic world involving these huge universe bubbles that once again might form because of quantum effects. And while extremely recently, one of the first attempts to recreate this was already conducted by the scientists from Italy. In this case by using ferromagnetic superfluids. And their experiment so far seemed to be kind of positive. They potentially saw these bubbles form, appearing as individual lines inside their experiment. But they appear as lines because this is basically a one-dimensional experiment that does not possibly represent the actual universe just yet. In other words, they do show that something happens here on a quantum level, with the formation of some kind of a bubble-like structure, but it's quite possible to interpret this experiment in maybe different ways. Still, an interesting first attempt. And because of the observations from this experiment, several other teams are already planning a new experiment, a more advanced version, potentially using at least 2 dimensions, in order to see if they actually get the same results. Here the scientists want to use potassium atoms to once again create Bose-Einstein condensate. And once the cloud forms and starts to act as a single quantum particle, their math predicts that it should actually start forming these miniature vacuum states inside of it, lasting for several seconds. And at least mathematically, they seem to actually be very similar to the bubbles that formed the universe, at least in the idea involving the inflation theory and the multiverse. Here they actually expect to observe exactly what happens to these vacuum bubbles, how they interact with one another, what they actually produce inside of one another, and also see the end of the bubbles as well. And it's really the interaction in this case that they're most interested in. Because by then seeing how these bubbles interact and comparing them to what potentially happened with the universe, the idea here is to then see if this is what we actually observe in the CMB as well. So if certain bubbles form in clusters, they might produce similar effects to what we theoretically might detect in the cosmic microwave background, with the results available in 2024 possibly helping us understand if there's anything in the CMB after all, or if it's all just far-fetched and there's just one single universe. Intriguingly though, if there are discoveries in this case, it might also help us understand what happens to the universe at the end. It might also help us understand how the interaction between various universes might end up producing specific types of gravitational waves, possibly detectable through various studies, and just generally explain why exactly the universe formed, how it evolved over time, and what the interaction with other bubbles might have done to it as well. So definitely big questions, potentially big answers, but still at the moment extremely hypothetical, and really nobody knows where any of this goes just yet. But honestly, this is a really exciting study, or at least a future experiment, and so far these preliminary results from the Italian study definitely make this a really exciting opportunity to possibly learn so much more about the universe than we ever could before. And so I'm definitely going to be coming back and talking more about this once the experiment itself starts, or once similar experiments from other scientists discover something else in the process. Either way though, just the fact that someone discovered a way to potentially study the entire multiverse by just studying the tiny effects inside super cold gas is already kind of mind-blowing. Although here, we obviously have to be really careful. Interpreting the results and trying to make the connections, that's going to be the hard part. This is actually where most of the arguments and most of the disagreements are very likely going to be taking place. But for now at least, cool stuff, cool ideas, and cool propositions. Hello Info Person, this is Anton, and today we're going to be discussing this relatively new and somewhat intriguing paper that might have discovered something really unusual about the universe. Something that nobody expected. The universe, or at least the early universe, might have not really been symmetric, or in other words, it seemed to have some kind of a preference in terms of what we usually refer to as handedness, or I guess symmetry. Or to give you, I guess, a slightly better, more realistic explanation, if we were to create a bunch of stuff in the entire universe, we would assume that the equal amount of inverse or mirrored stuff would exist as well. So for every particle you'd find an antiparticle, and for every particle-antiparticle pair, they would essentially resemble mirror images. Although in this case, this particular mirror image can refer to any property. Here's an example of a mirror image of charge, with the expectation being that we generally expect the universe to have both in equal amounts in order to basically make sense. But in particle physics, there are other types of symmetry, including something known as parity, which to some extent refers to handedness, or which way a typical particle would be spinning. And so overall, for many years, scientists expected all particles to basically be symmetric in every single way. But in physics, there's also something known as CP violation, referring to certain unique violations of symmetry in certain types of particles. We've actually discussed this in one of the previous videos, but there was a discovery back in the 60s that eventually led to the Nobel Prize, with the actual story being a little bit more controversial, with the main point being that CP violation, or the violation of the symmetry, seems to exist in certain subatomic particles around the universe. But if you want to just read about this, you can also read the article about the so-called Wu experiment. This is a pretty intriguing story, and in essence shows us that something is actually going on in a universe after all. But in this case, this was very small scale. as in it showed us that certain particles seem to have violation of symmetry, but the vast majority out there seem to not. Most of the stuff seems to be symmetric. And by itself, this presents a small problem. The problem being that, how do we explain how everything actually exists? Or basically, why are we even here? If the majority of stuff out there is symmetric, and if all particles are actually equal to their mirror images, and they were produced the same way in the beginning of the universe, well, in that case, Big Bang should have produced equal amounts of everything in the universe, and that includes matter and antimatter, and it would only exist for a fraction of a second, annihilating and leaving energy behind. Or just to rephrase this, if the entire universe was actually symmetrical everywhere, technically everything should have been gone a long time ago, with all the particles annihilating in the process. If symmetrical, the universe should have produced an equal amount of matter and antimatter, and so something here just doesn't add up. Even though a lot of things in the modern universe seem to be symmetric, maybe this was not always the case. Maybe the early universe was asymmetric, thus explaining how matter was able to survive so long, and why there is more matter than antimatter, with everything eventually becoming symmetric over time. And that's of course something that has been confirmed. For example, we know that all electromagnetic forces seem to be symmetrical, and no asymmetry has ever been observed. But we also know that electromagnetism did not exist for the first few moments of the existence of the universe, with the electromagnetic force even connected to something known as the weak force, which we know contains asymmetrical features, which already hints at the potential asymmetry of early universe. But all of these so far are just hints and just theories. Is there any physical evidence? Do we have any evidence for any of this, or is it just as theoretical as dark matter? And it looks like the paper behind me points at this really strange evidence, something that currently has absolutely no explanation. So let's discuss this in a little bit more detail, talk a little bit more about how this was discovered, and what ramifications this might have. First of all, the title here is obviously a little bit long, but in a nutshell what the scientists did here was sort of intriguing and really interesting. They essentially realized that when it comes to mirror images, or basically parity, the most simple three-dimensional shape whose mirror images are going to be different is a tetrahedron. Or in other words, a tetrahedron is the simplest possible shape that cannot be rotated into its mirror image in 3 dimensions, the simplest 3D shape that has unique mirror images. And so the scientists behind this paper wanted to see if, well, hypothetically, can we actually discover a bunch of these tetrahedrons out there in the universe and see if the overall amount of them is going to be more or less equal, basically left-sided or left-handed and right-handed, or if there's going to be some kind of a preference. Is there going to be a larger number of, let's just say, certain tetrahedrons compared to other ones? Just for the sake of simplicity, let's call them left-handed and right-handed. And obviously modern theories and modern understanding of the universe suggest that they should be equal. No matter where we look, we should see equal amounts. And that's independent of what we look at. And so how do we even look for these tetrahedra out there? Obviously we're not going to be able to find specific shapes or specific stars of this shape. Well, what they did was kind of brilliant. They realized that you can actually connect this to various galaxies, specifically distances to galaxies compared to one another. In this case, this tetrahedron is formed by 4 separate galaxies, with the distance between each galaxy represented as R1, R2, and R3. And as you can see from the formula, R1 is the smallest distance, R3 is the largest. Or just to rephrase this, they looked at quadruplets of various galaxies out there. And the only thing that they had to know about these galaxies was the overall distance between them based on various redshift calculations. But to make calculations and observations much easier, they focused on galaxies known as LRG, luminous red galaxies, and specifically 280,000 such galaxies from the Baryon Oscillation Spectroscopic Survey and 800,000 other observations from a slightly different survey that was conducted by the same program. So basically they looked at over a million very bright galaxies whose properties were quite well known. And then they created these hypothetical 4-point correlation functions out of all of these galaxies. This actually created something like million trillion different possibilities, all based on 3-dimensional vectors formed by individual galaxies. Now once again, in theory, we should expect pretty much equal amounts of these left-handed and right-handed tetrahedra, no matter what kind of galaxies you look at, no matter where they're located, simply based on the idea of random distribution of matter across the universe. Now there might be some chunks slightly more concentrated than others, but as you average everything out, it should be more or less equal. But once they applied mathematical analysis to all of this, they discovered that in the first sample, the actual evidence for non-symmetry was really significant, specifically 3.1 sigma, which is already a huge discovery when it comes to new physics, with the second sample producing something even higher at 7.1 sigma. And none of this can be explained by modern theories of gravity, any kind of evolution of the universe, expansion of the universe, or even more hypothetical, less accepted theories. Or just to rephrase this, there is absolutely no explanation for why this was detected. No idea why there seems to be symmetry when it comes to galactic distribution. However, they do believe that this is maybe something that happened right after the Big Bang, potentially during the inflation period and before the fundamental forces became the way they are. And so as the universe suddenly expanded, for some reason, it seemed to have some kind of a preference for certain symmetry. And then, as the universe evolved over time, and as things like cosmic web provided the foundation for new galaxies, over time all of these new galaxies started to position themselves in what seems to be preferred type of a symmetry, creating a kind of a symmetric imbalance. Although the actual source of this symmetry is obviously unknown and will be currently impossible to determine. And because of this unusual, somewhat groundbreaking discovery, it's also important to talk about potential errors. And while in terms of errors, there might be some bias here, as in observational bias. So far this is all just based on the release from SDSS and just 1 million galaxies out there. We've actually discussed this previously, but the release from SDSS so far only covers this much of the universe. So basically it doesn't cover the entire universe around us, mostly because of the way that these telescopes work, where they usually look during nighttime, and how certain regions become somewhat unavailable. And so in theory, maybe it's just in these locations that things are slightly more sided. Maybe if we look here, for example, or over there, the actual sidedness will suddenly disappear. But at the moment this is really the only bias I can think of, and the only problem I found in this particular interpretation. There is, however, a solution to all of this in the future. Other galactic surveys, such as Dark Energy Spectroscopic Instrument or ESA's Euclid telescope that's going to be launched sometime in 2023, are extremely likely to provide even more data to either prove this and find even more weirdness, or completely disprove this and discover where the mistake actually was. And so whether this was just bias that can be resolved by these telescopes, or whether this is actually something fundamental discovered here, we'll unfortunately only know in time. But until then, this is a pretty big discovery, and actually a somewhat unusual discovery that doesn't really have a very good explanation just yet. But the implication here is that if the universe was handed in the first few moments of its existence, it seems to be still visible today, and more importantly, it might finally explain why we're even here, why matter prevailed over antimatter, and why physical objects were formed over the last 13.8 billion years. But what other implications this has, I currently have no idea. When it comes to science, and I guess a lot of other things, including politics and including climate, 2023 was a pretty crazy year. Lots and lots of things happened, and some of those things were maybe not so nice. But in terms of actual announcements from various government agencies, from various scientific communities, or even scientific discoveries in general, this year was really extreme. I mean, just look at some of these stories recently. We had the room temperature superconductor, which by the way we're going to be discussing really soon once again, because this story apparently did not finish yet. But yeah, as you probably learned from the previous videos, it was basically bad science. We also had some really unusual stories in regards to UFOs and aliens, including the Mexican aliens. Side note, also not real, but we'll probably talk about this one day in the future. And we of course had those UFO hearings from the US, with even NASA at some point joining in and creating a committee to investigate all of this. I haven't really talked about it much, mostly because it's just not very interesting and it's going to lead nowhere. But we'll discuss this later, I promise. And so here we are, almost at the end of 2023, and it looks like we have maybe one more story to talk about. The story that just came out, and the story that is also maybe not going to go well scientifically, but is still really interesting to investigate, just because of the sheer scope of what's been achieved so far. Today we're going to be talking about the concept of the impossible drive, or more technically, quantum drive, the mysterious engine that is able to produce propulsion without any fuel. And actually before I start, there's a video in the description that actually talks about the EM drive studies in quite a lot of detail. Do check it out as well, because it covers the other topic really well. But today we're not discussing the EM drive, we're actually discussing a somewhat different proposition that actually does involve physical explanations and, I guess to some extent, real science, but also a proposition that might actually have a few mistakes in it. And so, hello wonderful person, this is Anton. Let's discuss the idea of quantized inertia once again, and let's talk about the quantum drive that is literally now in outer space. It's actually physically there, and you can even track it yourself by using one of the links in the description below. But before we talk about this mission and what's being tested, let's start with a bit of a theory, because this is really important for understanding what's actually happening here. And here the story starts with this British professor, Mike McCullough. He essentially proposed a somewhat interesting explanation involving inertia as a concept. I mean, we sort of understand what inertia is and I guess how it works, and Newton explained everything here mathematically really well. I mean, by itself, inertia is defined as a tendency of an object to stay in motion or to stay at rest unless there is some kind of a force applied to it. You push something, it starts moving, and it's going to keep moving unless something pushes on the other side or pulls at the object to make it stop. And though Newtonian physics explain inertia in terms of action and in terms of what happens to objects, it doesn't actually explain why it happens. As in, why exactly do we have to push something in order for it to move? What's stopping it from moving by itself? And so, unlike in the regular inertia, the idea of quantized inertia in essence tries to connect relativistic ideas with quantum ideas and then explain Newtonian physics. And by itself, the initial explanation, when you hear it, makes quite a lot of sense. And so here is roughly how it's explained. You might be familiar with the idea of the event horizon around black holes. It's essentially the point of no return. Nothing can escape the event horizon, which as a result creates the blackness of the black hole. With the exception of the mysterious Hawking radiation, which is believed to be produced around the black hole as a result of quantum physics. Here, sometimes, a particle-antiparticle pair is created in such a way where one of the particles escapes, other one falls into the black hole, resulting in the production of actual radiation, and also taking away a little bit of the mass from the black hole itself. You can learn more about this in one of the videos in the description, but in a nutshell, Hawking radiation has been physically proven using various analog black holes. This image is actually from a study using analog sound black holes that were able to produce Hawking radiation. This was discussed previously in one of the videos right there. And so when it comes to black holes, event horizon and Hawking radiation have almost certainly been proven by using various analogs. But something extremely similar technically happens all around us at the edges of the observable universe. Because here, due to the sheer expansion of the universe at some point, right at the edge, things are expanding much faster than the speed of light. And so it actually creates another type of a horizon. But it's not called event horizon, it's known as the Rindler horizon. The horizon all around the universe that to some extent acts as the actual event horizon of the universe. But here, let's imagine this. We're going to start accelerating toward one single point into one direction in this three-dimensional sphere. And as we're moving across here, we're going to experience a kind of a shift in the Rindler horizon. In other words, the sphere itself is going to start shifting, but because we're accelerating, it's also going to shift the Rindler horizon in this way. If we accelerate less, the Rindler horizon expands, and if we stop, it goes back to where it was originally. Mike McCullough has a pretty good explanation about this in one of his blogs in the description. And so in essence, the idea here is that this event horizon moves as we accelerate into a certain direction. But here's the thing. Just like with black holes, this event horizon has its own Hawking radiation, and it's known as the Unruh effect or Unruh radiation. And the proposition here is that, well, when you accelerate into a certain direction, you're actually going to experience more of those particles hitting you because of the Unruh radiation. In other words, very similar concept of particle-antiparticle pairs, or basically Hawking radiation, is going to also occur as you accelerate in a direction because of this Rindler horizon or the event horizon of the universe. Or just to make it super simple, as you accelerate this way, you'll basically start getting more radiation into your face coming from the universe itself, coming from the horizon itself. And this, in terms of quantum physics and in terms of relativistic physics, is kind of sound. It sort of makes sense. But it hasn't been physically proven yet. There are physical experiments that are trying to discover if Unruh radiation exists. Once again, you can find out more about this in one of the videos right there. But for now, we don't really know. But based on this principle, McCullough essentially proposes that, okay, well, maybe this is actually how inertia works. If you push the object this way, the Unruh radiation pushes back and creates inertia. If the object starts accelerating, because of the pressure from the Unruh radiation, it has to constantly create acceleration using propellant, which in essence, to some extent, explains inertia as an actual physical force by using quantum mechanics and by using gravitational theories. And when most people hear this explanation, it sort of, I guess, blows their mind and it suddenly makes a lot of sense. But here's the problem though, actually there's maybe a couple of problems. First problem here is that, in terms of the actual physics, unknown radiation is believed to be extremely weak, like we're talking about imperceptible. As in, you have to create accelerations of ridiculous proportions, basically something that only atoms experience, in order to even feel 1 degree of difference or even to feel just a little bit of radiation. Which is why trying to prove this experimentally so far has been almost impossible. And because of this, most scientists do not think that it explains inertia at all. And the second problem, and I guess a much more serious problem, was the fact that back in 2019, someone actually found mathematical errors in the original proposition that have not been addressed since. And so for all we know, this quantized inertia principle, even though it sounds kind of interesting and sort of unique and very cool, might have been just a miscalculation and some kind of a mathematical error. But McCullough still believes this idea, and so do a lot of other people. And here's the thing, they actually conducted a few experiments. But not experiments involving unknown radiation or trying to discover it, they conducted experiments based on some of the propositions in their theory. And the proposition is basically, just like with the EM drive, you can use this inertia to physically create propulsion inside a certain shape by using nothing but electricity. In other words, you can create a no propulsion drive, the impossible drive, or in this case, the quantum drive. And that is why a few years ago, McCullough actually got a grant from DARPA to try to investigate this, even though maybe the physics did not work out at first. And so they actually physically started doing experiments, and a lot of them potentially might have been positive, as in they actually maybe produced propulsion. But as you might have learned from the video on the EM drive, we know that sometimes this is just a bias or even some kind of a mechanical problem, the problem that was discovered with the EM drive as well. And so what's happening here? Well, to be honest, we don't really know. But one of the US companies basically tried to test it as well and potentially might have found positive results as well. And well, they didn't just test it in a lab, they then decided to send it to space. And so the company known as IVA Limited, in collaboration with Rogue Space Systems, basically managed to launch their project on a SpaceX rocket. With the project itself resembling something like this. It's basically a CubeSat that inside of it contains this unusual quantum drive engine that unfortunately we know very little about, because in this case the company keeps it hush-hush about how exactly it was made and what the structure of it is on the inside. They're basically making it a patent. I mean, their IVA quantum drive, if it works, would be obviously groundbreaking. And if it doesn't work, it just means that 2023 was just a year of a lot of fluky, unusual science. But for several days now, this satellite has been essentially active in space and has been getting ready for its relatively long experiment. With the experiment in this case being super simple. It's just going to turn on the engine, which only requires electricity, and if everything works, it's going to use the effects from quantized inertia to acquire a tiny amount of boost. But how much of a boost? Well, basically just as much as the EM drive. Every single watt of electricity is supposed to provide 52 millinewtons of thrust. And that actually beats the very efficient Hall effect thrusters, or basically ion engines, currently used in a lot of different NASA missions. It would be essentially 60 to maybe 80% more efficient, and more importantly, not require any fuel. Ion engines do require, for example, xenon, which can run out after a few years, and are also very massive and extremely large in size. In comparison, the quantum drive would require no fuel, only electricity, and would only weigh approximately 200 grams, or about 7 ounces. And so right now, honestly, this is maybe one of the most exciting missions in outer space, and at least in theory, once again, just like that superconductor, may finally lead to some major discoveries. With a little bit of a caveat again. It might all be based on bogus science. Even though the engineers behind the startup did confirm that they tested this in every single way on planet Earth, and don't think that the effects they observed were from any biases or from any interferences. In other words, they actually did measure thrust and cannot explain why. But that was on Earth. If it works in space, now that's going to be a tremendous breakthrough. That's basically going to transform everything. But will it? Well, we're probably not going to know until 2024. It's actually going to take several weeks to collect all of the data, and that's actually just to set the baseline for what's happening. And then in 2024, they're going to finally begin the experiment and start official measurements. And obviously, if the mission is successful, yeah, let's start packing our bags, we're going to Mars. Although I guess you can go to Mars, I'm gonna go to Titan, that's my favorite. But if it's a failure, the satellite does not change its orbit, no thrust whatsoever, which I think might actually happen, unfortunately. But yeah, let's not be too negative. I mean, I do want to believe. And so yeah, if the results are negative, well, for this particular startup, it's technically still not bad news. They basically did all of this as a kind of self-promotion. It basically shows everyone that they can go from a crazy idea to an actual physical test in just a few months, which is precisely what happened here. But in reality, right now, nobody really thinks it's going to work. And there are so many reasons why this is so. For example, this paper from 2015 specifically explains why nothing like this should work at all. It directly violates laws of thermodynamics. Likewise, previous experiments by various teams potentially discovered that all of the measurements here might have been the result of the interaction with the magnetic field of planet Earth. And so there was no thrust, it was just the magnetic field doing something funny. And so at least for now, I think I would see this as, I guess, a fun attempt, an interesting experiment, and definitely something really cool, but most likely not something super groundbreaking, as we'll discover in the next few months. And yeah, we'll definitely be talking more about this once there are some updates. Hello wonderful person, this is Anton, and today we're going to be discussing a relatively intriguing proposition and a somewhat interesting explanation for how in certain conditions, such as for example on the Saturn's moon Titan, we could actually have very unusual chemical effects entirely created by quantum physics, which at least in theory could even produce effects very similar to what life does right here on planet Earth. In this case, using a scientific phenomenon referred to as quantum tunneling. But more intriguingly, we're also going to be discussing several other studies that actually sort of imply that all of this also affects us right now, you, me, and everything around us, in a way that we don't actually realize, and in a way that we didn't really know about up until relatively recently. So let's discuss this a little bit more, but first I guess let's start with Titan. So why Titan, and why exactly quantum tunneling? Well, you might be already aware that the moon Titan is one of the most exciting objects in the solar system, except for, of course, planet Earth. It's the only other object we know of that has really complex liquid cycle, including liquid oceans and lakes. It also has a relatively thick atmosphere filled with things like ethane, methane, and potentially a lot of other hydrocarbons, and overall is filled with a lot of organic compounds that we usually associate with life. But in this case, there's a small problem. It's super cold here. And so the liquid cycle is not water, it's actually ethane and methane, and the temperature is approximately minus 180 Celsius or minus 290 Fahrenheit. In these frigid conditions, we don't expect a lot of chemistry to take place, especially when it comes to organic chemistry and when it comes to creation of things like DNA. But even though at low temperatures of Titan, there might not be enough energy in order to force these reactions to happen, in theory this could be overcome with quantum physics. And specifically the physics we're still learning about, but the physics that we know life already depends on anyway. For example, quantum tunneling is the reason we have things like nuclear fusion inside the sun. All of the heat produced from the sun, with all of their hydrogen fusing and producing helium, is actually a result of quantum tunneling and not any classical physics at all. And there are quite a lot of different articles that analyze this, and time again the calculations suggest that the only reason we have nuclear fusion inside the sun is because of individual hydrogen atoms occasionally experiencing quantum tunneling effects and creating helium, literally allowing particles to pass from one location to another almost instantly and thus merge into something else. And that's of course, a lot of small particles are not just particles, they also start acting as waves. And in this case, it allows various things like electrons or atoms to pass through potential barriers that they would not have energy to pass through otherwise. In other words, just like the image right here shows you, a particle can actually go through a wall as long as its probability wave can reach the other side of the wall as well. It doesn't happen to all of the particles, but there's always a small chance. And intriguingly, a very similar phenomenon can actually drive relatively complex chemistry on extremely cold objects like Titan. It might even become the main source for a lot of chemical reactions around these super cold objects. And so in this case, when a chemical reaction requires a transfer of proton or electron, it can actually easily happen using quantum tunneling and not necessarily classical chemistry. And even though in this case the scientists haven't really officially simulated actual reactions yet, when they performed simulations of chemical reactions in Titan-like conditions, their general simulations so far have been very promising. Which means that when it comes to prebiotic chemistry, or chemistry that eventually results in life, there's actually a really high chance that this is the only way these reactions can occur in these very cold conditions. But obviously all of this might sound a little bit too far-fetched, or at least extremely unlikely, because obviously we don't really see quantum tunneling in real life very often, and we don't actually see things jumping through walls, or spontaneous chemical reactions happening all at once. And so is this all then kind of far-fetched and potentially hypothetical? Turns out, not at all. And this is coming from a lot of other studies on even things like our DNA. Now, it's already been established that, for example, birds very often use quantum effects, and specifically the entangled state of various magnetic particles inside their eyes, to sense the Earth's magnetosphere. It's also been established that photosynthesis also seems to depend on quantum effects inside the molecules of chlorophyll, as tiny particles are somehow able to achieve a state of superposition in order to find the correct path. So life definitely found ways to use quantum effects already. But it gets even stranger. Several recent experiments in the last few years started to discover that tunneling also takes place in DNA of pretty much all life on the planet, allowing certain atoms to break through energetic barriers and combine into something else. And you can find several papers in the description that deal with this concept quite directly, the concept of DNA transforming not through some chemical reaction or through classical chemistry, but entirely through quantum effects. One of the first such observations was back in 2021. The observations of spontaneous mutations inside DNA, where the hydrogen molecules would jump from one place to another and thus changing the DNA just a little bit. And although one or two such jumps would not really affect DNA permanently, because the scientists believe so many happen all at once, this does actually dramatically change DNA structure over time. In other words, it implies that the mutation process itself does not even require anything from the outside. It happens naturally, spontaneously, without presence of any radiation, any chemicals, or anything else we usually associate with mutation. And although in this case they were only able to model very small strands of DNA, focusing on very specific pieces, with the effects only visible in small parts, at least in theory, the scientists believe this would happen everywhere inside the DNA molecule. Unfortunately, the current computers are not actually powerful enough to try to simulate this just yet. At the same time, they also discovered that certain bonds, for example AT bonds inside DNA, are much more likely to mutate using the process of quantum tunneling compared to GC pairs, simply due to the strength of the bond and due to the location of hydrogen, which implies that quantum tunneling might drive certain types of mutation, but not other types. But I guess more intriguingly, a similar paper from 2022 discovered something else even more unusual. It turns out that the rate of mutations through quantum tunneling is possibly several hundred times higher than previously believed, possibly even resulting in a lot more mutations than classical mutations, which sometimes happen with hydrogen atoms jumping from one location to another because of the overall motion of DNA. Now, it doesn't mean that this is the most powerful type of mutation, but it just means that it's way more potent than anyone imagined, and the actual chemical reactions resulting from quantum tunneling are dramatically more powerful than anyone thought possible. So in that sense, it definitely affects you, me, and everyone around us, even without anyone realizing. But what about other types of chemistry? Well, this is what this recent paper decided to investigate as well. They wanted to find out if all kinds of chemistry can actually happen through quantum tunneling. And in this case, the main focus was, once again, hydrogen, simply because this is the type of chemical reactions we would expect on objects like Titan. And so in this case, the scientists wanted to observe if the interaction between hydrogen and deuterium atoms would be mostly driven by classical chemistry, or if the atoms would also be affected by quantum tunneling as well. And so here, by taking cooled down deuterium and hydrogen, they expected the hydrogen molecules to be a lot less likely affected by the interaction with deuterium ions. Or in other words, they expected the hydrogen molecule to remain as a molecule and not turn into some kind of a hybrid or an atomic hydrogen, something that normally occurs when there's deuterium ions around. But by looking at this mixture, after 15 minutes of interaction, they were able to discover that the actual composition was a little bit different from what was expected from classical physics, implying that once again tunneling has occurred, allowing chemical reactions in these very cold conditions, although the actual rate was pretty low, possibly only one event for every 100 billion collisions. Nevertheless, it was definitely happening, and clearly suggested that similar chemical reactions can take place around other objects, including Titan, or a lot of other super cold places in the solar system. Thus kind of confirming that we can have organic chemistry pretty much anywhere in the entire universe, independent of what the actual conditions are. Now these would be not very fast reactions, they would be actually super slow, but given billions of years, and stable enough environment, quantum tunneling, in theory, could produce something similar to what we have on Earth. Now obviously this is all very theoretical, and we're not going to know more until we actually go to Titan, which is expected to happen in the next 10 years. But nevertheless, these actual discoveries with physical experiments teach us something that we kind of never really knew before. Quantum tunneling, and specifically quantum chemistry I guess, is a lot more influential than anyone thought possible. Which of course means that we're probably going to be coming back to this idea a little bit later, specifically once there are more studies and more research, just because I'm now super curious to discover what the scientists find next. Hello wonderful person, this is Anton, and in this video we're going to be discussing a confirmation that there doesn't seem to be anything wrong with the modern ideas of particle physics. The standard model of particle physics, at least for now, seems to predict the world pretty well. At least the parts that it's supposed to predict. But I guess more specifically, we're going to talk about the recent discovery, or I guess rediscovery, coming from a very important particle physics experiment known as the ATLAS. Part of CERN and part of the Large Hadron Collider, the largest particle accelerator in the world. And in this case, it's actually in regards to something we've discussed last year that to some extent created a huge problem for the particle physics when it was originally reported back in the middle of 2022. And in this case, it's actually in regards to something we refer to as W boson, with the 2022 discovery being that the actual predicted mass versus calculated mass for this unusual subatomic particle, as reported by the younger Anton right here, might have actually been somewhat off. This picture right here kind of shows you the predicted value seen as a black bar and the observed value from the 2022 experiment. And even though the actual difference was very minute, specifically 80.379 versus 80.433, because of the previously accurate observations from other experiments, this created a pretty big issue. The issue being that nobody could explain what's actually causing these discrepancies, and as reported back in 2022, this basically implied that the standard model of physics, or particle physics, might have been either incorrect or was missing something crucial that nobody had an explanation for. And this was a pretty big deal. All of these super expensive, super powerful particle accelerators have already reached such a tremendous accuracy that all of them have been producing extremely accurate results that were more or less consistent across the board. Yet suddenly one of them produced something that was kind of off. And this wasn't really adding up and could not be explained right away. For particle physics, or actually a lot of physicists in general, this was a huge deal. A lot of naysayers of particle physics already started using this as an excuse to basically say that the entire model is incorrect. But that's not really science at work, because science at work is doing science again and again until you actually see what's happening, and specifically trying to see if the results from that last year's experiment were actually correct. And that experiment was conducted by the Fermilab inside their particle accelerator known as Petrov, which, though not as powerful, did operate for much longer. Although more specifically this was part of the CDF, or Collider Detector at Fermilab, the international collaboration has been going on for a few decades now. Once again, you can learn more about all of this in the video in the description from last year. Oh hey, what's up, younger Anton? Anyway, so as you can probably tell from the title and from how I started this video, this, or I guess this, was possibly incorrect. Even though last year's prediction suggested that the W boson might have been a little bit heavier, using a completely new technique and new analysis, the scientists using much more powerful CERN definitively confirmed that there doesn't seem to be anything wrong with our models or our predictions. The particle's mass is a close fit to the standard model's predictions. Or in other words, there doesn't seem to be anything strange here, nothing weird to see here. But in this case, I think it's also important to understand the ramifications, or why all of this is measured, and what exactly we're trying to learn here. Or I guess more specifically, what is W boson? What exactly does it do around us? And why is it so difficult to measure its mass? So here's actually the intriguing part, or something that's kind of counterintuitive, which also sort of highlights how ridiculously unusual and still somewhat difficult to explain various subatomic particles actually are. The predicted mass of the W boson, which is once again about 80,379 megaelectron volts, is more massive than the proton, the neutron, and in some cases even certain atoms like iron. But none of this really matters because these subatomic particles exist for just a fraction of a second, and they only seem to have one single role. They mediate what's known as weak interaction, also known as the weak force, one of the four fundamental forces. So, for example, they can be responsible for changing one atom into a slightly different atom. For example, nuclear decay, such as transformation of one atom into another atom, is entirely driven by this particular subatomic particle, when, for example, an atom of iron turns into an atom of cobalt. But the actual process happens on a much smaller scale, inside neutrons, when one of the down quarks can spontaneously change into an up quark. This particular process seems to be spontaneous and sort of random. And when this happens, it releases this really massive particle the scientists now refer to as W boson. A particle that was very hypothetical until its confirmation decades ago, and eventual confirmation for its mass and what it seems to do inside various subatomic particles. But this boson exists for a fraction of a second, then becoming an electron and an antineutrino. As a matter of fact, this is one of the main ways neutrinos are produced around the universe. With neutrinos, by the way, being a separate topic we're going to be discussing really soon, because these are very mysterious and also very important particles that might one day explain a lot of things. And so in this case, W boson is a kind of a mediator. But because of its really short existence, and because we don't physically see any of these particles and can actually only measure them by conducting various particle collisions and then seeing interaction of subatomic particles, while using a lot of statistical prediction to try to see what's going on here, in order to produce more and more accurate results, the scientists needed several things. One of those things was conducting more and more experiments and getting more and more data, something they've been doing now for several years. But the other thing that was missing here was a statistical interpretation model for all of these results that were collected over the years. And so compared to the result from last year, this is basically what changed. The scientists applied a new statistical model, reanalyzing a sample of 14 million W boson candidates, usually produced during proton-proton collisions, with this revised statistical approach improving on the results dramatically, with their new findings potentially being about 16% more precise than any previous detections. But I guess more importantly, calling into question 2022 results from the Tevatron Collider in the US. In this case, they actually had some additional results from 2017 to validate some of their findings, bringing the total measurement very close to the predicted value of 80,357 mega electron volts. Their value was 80,360, so just a tiny variation. And the thing is, this is a pretty important field of study, mostly because, well, of the thing behind me. Technically, the Sun is the biggest nuclear reactor next to us and is potentially responsible for producing the most neutrinos in the vicinity. All of these neutrinos are produced, similar to the process I described previously, with the help from W bosons. Here's actually the first confirmation for the existence of neutrinos. We'll be talking a little bit more about this in a video coming out soon. But the thing about neutrinos is that they're ridiculously difficult to find and also to confirm. It took decades of research to finally confirm their existence, and certain neutrinos have still not been found at all, even though they should exist out there. And because they're so difficult to find and to catch, that's basically why W boson studies have also had a lot of difficulties as well. Mostly because W bosons dissolve into neutrinos as part of the fundamental theory. And so in reality, even though W boson by itself might not be super important, because they do produce neutrinos, which are believed to be everywhere, with like billions and billions of them passing through your body right now every single second, but actually not doing anything to you, trying to understand exactly what these unusual particles do in the universe and how many of them there are, is of course one of the main reasons for a lot of these experiments. Or at least one of the main reasons I'm interested in this, mostly because neutrinos have also been proposed as an explanation for many different mysteries across the entire universe, and a very specific type of neutrinos might also once and for all confirm the Big Bang Theory. And we'll actually be discussing this very soon in the video that's going to be coming out in the next few weeks. So subscribe if you'd like to learn more about this particular topic. And so in the end, at least for now, it looks like the particle physics is somewhat correct. And more importantly, all of the subatomic particles predicted by this model have been more or less accurately measured by various experiments. When it comes to the existence of the universe and the formation of the universe, there are still a lot of unresolved questions, a lot of mysteries that we just cannot explain. Some in regards to things like dark matter and dark energy, but some are even more fundamental. Why does the universe even exist? Technically, because of the existence of what's known as antimatter, none of the physical matter inside the universe should even be possible. With the actual argument going something like this. We know that universe contains both matter and its opposite, antimatter. The existence of antimatter was physically proven back in 1932. This is a very famous picture of the first ever positron. And we know that when matter collides with antimatter, it annihilates, creating nothing but energy. And so if that's the case, when the universe was just formed, it very likely possessed both matter and antimatter in equal amounts. And if that's the case, all of this matter and antimatter should have self-annihilated, basically forming nothing but energy. Yet we have things like planets and stars to provide the evidence of the opposite. For some reason, matter prevailed, antimatter did not. For some reason, one dominated the other. And this is actually one of the bigger mysteries in physics that is still completely unresolved. Although some of the modern theories propose that this is a type of what's known as CP violation, or violation of symmetry inside the particles, with one of the best explanations for this being a hypothetical, still undiscovered particle known as axion. It just so happens that this is also the same particle that might be responsible for the dark matter. Now that by itself has not been proven yet, but that's basically the idea here. Mysterious invisible particles potentially cause matter to be more prevalent than antimatter. But in order to basically solve these mysteries and to actually try to understand what's happening with the antimatter, a lot of scientists have been proposing different types of experiments. And one intriguing experiment that scientists wanted to conduct is to actually see if there is something called antigravity. Or basically, do antimatter particles experience gravity in the opposite way? Because if so, this actually changes everything. If for some reason antimatter feels antigravity, this can suddenly provide us with a lot of other explanations for why antimatter seems to be so rare and matter seems to be so common. The axions would no longer be required. Because if antimatter experiences antigravity, and if the positron is being pushed away by gravity instead of being pulled by it, this would explain how matter and antimatter got basically divided in the early universe. That way, in one side of the universe you would probably have a lot of matter, on the other side you would have a lot of antimatter. And since we know that particles and antiparticles mostly have the same properties except for their charge and a few quantum numbers, it means that they can actually create their own anti-gas, anti-stars, anti-planets, and potentially even anti-galaxies. So that explanation, assuming that antigravity is real for antiparticles, would imply that the entire part of the universe contains a lot of anti-galaxies and maybe even anti-life. Cool proposition, but requires some evidence. Which is exactly why this particular experiment has now been completed, providing definitive results, but also being one of the most complex physics experiments that humans have ever performed in the last decade or so. Observation of the effect of gravity on the motion of antimatter. Performed by the scientists from CERN, the largest particle accelerator, but inside a specially designed facility known as Alpha G. Now this experiment is absolutely mind-blowing in terms of its complexity and in terms of what was achieved here and how it was achieved as well. But before I explain to you what's happening here, let's talk about some of the properties and the details of antimatter, because it will help you understand what the scientists were trying to work with. So first of all, unlike regular matter, antimatter is exceptionally rare everywhere. Ever since the early experiments, if you were to add up all of the antimatter into one large chunk, we've only been able to produce a few nanograms. That's ridiculously small. Intriguingly, not so long ago, NASA discovered that quite a lot of antimatter is being produced in our atmosphere by a lot of different effects. One of them is obviously collision of cosmic particles with the upper atmosphere, but the other stranger effect comes from the lightning. Thousands of lightning strikes per day seem to produce gamma rays with very specific energies that can only be explained by the production of antimatter through the interaction of a gamma ray with another atom. And because we know that electron and positron production will always have the same energy, by detecting these coming from the upper atmosphere, we know that this is very likely produced by lightning and nothing else. Although here it's really only positrons, the antimatter of electron. Interestingly, quite a lot of antimatter is also probably stuck in the Van Allen's belts around planet Earth. And here it's most likely antiprotons. These are probably coming from the sun. And so at least in theory, this is one of the sources we could use in the future to try to capture more antimatter. But I guess that's beside the point. The point is that there is always at least some of it around the planet at all times. But the artificial production of antimatter has mostly been done in particle accelerators and is usually very expensive and requires a lot of energy. And once it's produced, it's also very difficult to try to store it. Any collision with a normal particle will instantly annihilate it. Only extreme locations like black holes and neutron stars are able to preserve antimatter long term. Here on Earth though, the record for preservation of antihydrogen is approximately 17 minutes. Although antiprotons can be stored a little bit longer, in this case up to 400 days. It essentially involves a very complex device that traps the antiparticles using electromagnetic fields. Super expensive, lots of energy required. Which is why antimatter is technically the most expensive stuff on the planet. $25 billion per gram. So, thinking of a new business idea? Yeah, try antimatter. At the moment, in a fully operational facility that's producing millions of antiprotons per minute, it would actually take billions of years to produce a single gram of antihydrogen. So yeah, we're definitely not even close to being able to produce this stuff with more efficiency. Which is exactly why it's so difficult to perform experiments using antimatter and to try to learn more about it. It's just really hard to make it. But as I mentioned, it's absolutely important to study it if we want to understand the universe as a whole. What exactly happened here early on, and where exactly is all of the antimatter that was supposed to exist here as well. And so this recent experiment known as Anti-Hydrogen Laser Physics Apparatus, ALPHA, is essentially a huge collaboration that's been running for several years, with a single purpose: figure out if antimatter feels gravity or anti-gravity. But how do you actually do that? Well, you obviously lift it up and see if it goes up or down. Easy answer, right? But how exactly do you measure this with tiny particles, especially if the force of gravity acting on a single particle is super weak and difficult to measure? Unless you make some kind of a larger object out of these antiparticles, it will be difficult to measure if they're falling or going up. Yet this is precisely what the scientists have been doing here for the past few years. They basically created a bunch of hydrogen atoms and antihydrogen atoms and put them in a tube that you see right here. Inside this tube they would be trapped for a very long time and would essentially experience only two forces: electromagnetism trapping them and gravity that would naturally be pulling them down. First they did this with hydrogen atoms, discovering that in the process, roughly around 80% of hydrogen atoms would exit from the bottom, with about 20% exiting from the top. Makes sense, that's gravity at work. But now they had to do the same with antihydrogen. Once again, same particle, just different charge and a few other quantum qualities. And so here, by measuring this over and over again for many years, they started to discover that it looks like antihydrogen is doing the same. The vast majority of antihydrogen particles were mostly exiting from the bottom, not from the top. And there's really no other explanation here than basically gravity at work. Although I guess interestingly, the actual number was maybe a little bit lower. I think it's something like 76% going down and 24% going up. And so what exactly does this mean? Well, obviously, first of all, it means that there is probably no anti-gravity, at least when it comes to antiparticles. They seem to still experience regular, down-to-earth gravity. And because here the only thing that was actually changed was the magnetic field, it will be very difficult to explain this as anything but the gravity. But there's still a very slight chance that maybe, because the results do not exactly match with normal hydrogen, for some reason, gravity might prefer matter over antimatter just a little bit more. Now these are just some preliminary discoveries and it doesn't actually mean anything yet. And to confirm this, these experiments would have to be repeated many times. But if confirmed, it does suggest that maybe there is an explanation for why the universe is the way it is without the use of, for example, axions. And so maybe, for some reason, antimatter is just a little bit different in its interaction with normal gravity. But that's not something we can actually establish right now, because what we can establish is that no anti-gravity at all. Gravity seems to work on everything for as long as it's some kind of a particle, even if it seems to be antiparticle. It also confirms that, in theory, antiparticles can feel gravity and combine into larger objects, even forming anti-galaxies. Anti-galaxies with pretty much exactly the same chemistry and physics as a regular galaxy as well. They would not look any different, but they might feel just a little bit less gravity based on these new experiments. With the only difference being that if they do collide with a normal galaxy, they'll basically completely annihilate, producing nothing but energy. As far as I know, nothing like this has ever been seen from anywhere, so their existence is extremely unlikely, at least in the visible universe. But based on the results from this experiment, it still means that we kind of are back to not knowing why the universe exists, or to be more exact, why it's made out of regular matter, and what happened to all of the antimatter. It looks like maybe we do need axions after all. And as I mentioned in the beginning, axions, at least in theory, could explain dark matter as well. Some videos in the description talk a little bit more about all of this. So definitely a super cool experiment, a very important discovery, and a confirmation that maybe, at least for now, antigravity is possibly not real. Although we'll probably learn more as the experiment keeps going and as more details are revealed about the properties of antimatter. At least for now, this is just super cool. I mean, honestly, just look at the size of this thing. This was designed specifically to study antimatter, an absolutely enormous complex, and possibly our first step of finally being able to produce this stuff in much bigger quantities. So today we're going to be discussing a concept that's kind of tricky, actually really tricky, because this concept is going to involve pretty much everything confusing about astrophysics. It's going to involve black holes, it's going to involve the expansion of the universe, and it's also going to involve quantum physics. But more importantly, it's going to involve the reality as a whole. Hello wonderful person, this is Anton, and today we're going to be discussing the study that as always you can find in the description below, that to some extent potentially explains why the reality exists. Or basically why you and I are physical objects that you can touch, you can interact with, objects and things that have properties much different from anything from the quantum world, where things are very undefined and involve concepts like superposition, where an object can actually have all properties all at once. Or, if we use a concept from the everything everywhere all at once, it's the everything bagel. Or basically, how do things turn from the everything bagel to a very specific bagel? Or if we try to describe all of this in more quantum physics terms, it refers to the idea of Copenhagen interpretation of quantum physics. Everything can be described as a possibility, until we're forced to interact with this something, or until it's forced to describe its actuality, and then it becomes a particle. Or in other words, things are an everything bagel until you measure or observe them, or until you interact with them, at which point the bagel becomes something else, acquiring one of its probable states, implying that quantum objects don't actually have any reality or any truth until they're observed or until they're interacted with. Although I guess the more common example in this case involves the cat in the box. The cat, while it stays in the box, is both alive and dead. When you open the box, the state changes. But what the scientists in this case are trying to answer is, what exactly opens the box for all of the particles around us? Or in other words, why is it that this actual cat exists, as do you and I? What causes the decoherence of everything around us? And in this case, by applying certain Einsteinian principles, the scientists in this somewhat hypothetical paper discovered something that could be potentially groundbreaking, if they're of course correct. For example, we know that quantum objects lose their quantum properties as soon as there's some kind of observation or interaction. But let's take this idea a little bit further and try to imagine that the observer is really far away from the object. Or let's just say that this observer is actually maybe in another galaxy, really far away. Well, according to quantum physics and according to pretty much all of the math behind it, this particular particle is still going to collapse because in this case the particle is entangled with the observer. It's going to create what's known as decoherence. And that's despite the fact that this observer could be thousands of light years away. Now it doesn't mean that the light in this case is traveling faster than light, it just means that, for some reason, when the information from one object reaches the other object, the quantum decoherence has already occurred. Or at least according to modern principles of quantum mechanics. Okay, let's go with our bagels again. Let's say this is an everything bagel really far away. But let's say that someone is actually looking at this bagel from a different galaxy. Quantum physics suggests that this bagel is going to assume a certain property and no longer be quantum. It's going to become, for example, a sesame bagel. But let's take this thought experiment a little bit further. What if that observer is somewhere else entirely? What if this observer crossed the event horizon and is now inside a black hole? Well, according to quantum physics, there's still going to be entanglement, but even though the light from the bagel is going to enter the black hole and cross the event horizon, according to Einsteinian's ideas, there's absolutely no way information from the black hole and especially all of this entanglement information, can then actually escape. Which to the scientists behind this paper created a bit of a paradox. Either quantum physics is wrong, which is very unlikely, or something needs to be solved with the general theory of relativity in order to explain this particular principle. But in one of the previous papers, the scientists behind this idea managed to mathematically solve this by assuming that the event horizon of the black hole itself, or that point of no return that no light can escape, actually starts acting as an observer itself. Or in other words, this right here could be the observer that causes decoherence and causes things to collapse. There was obviously no physical proof and no observational proof whatsoever, but in terms of logic and mathematics, it sort of made sense. But here's the thing though, if the event horizon of the black hole acts as a kind of observer causing things around it to collapse, it suggests that black holes around the universe sort of act like these giant observer eyes, potentially causing the universe to create reality that we know. Or the horizon from various black holes is responsible for creating physical objects and for collapsing quantum effects. And although that's an intriguing proposition, they actually go a little bit further in their recent study. In this case, realizing that these types of horizons, where nothing can actually escape, and things crossing the horizon sort of start violating certain quantum principles, may also exist elsewhere in the universe. As a matter of fact, the edge of the universe. Because in this case, pretty much in a sphere around us, there's this hypothetical idea known as the edge of the observable universe. Physically, we can actually never reach it, but hypothetically, the sphere around us, with a radius of approximately 45 billion light-years away from planet Earth, represents the observable universe. But right at the edge, because of the expansion of the universe, things are expanding faster than light. Or in other words, right at the edge right here, that's another event horizon. Sort of like the inverse of the black hole. This is usually referred to as the Rindler horizon, and more specifically the concept of the Killing horizon proposed by Wilhelm Killing to explain some of these observations. And I wanted to clarify that it's named after a person and not because it's killing anyone. And the idea here is that these horizons around us produce very similar decoherence of quantum states. Or the edge of the universe that's around us causes all of these everything bagels in the universe to become something else. Maybe a sesame seed bagel. Or to rephrase this even more, the edge of the universe acts as a kind of an observer of everything inside of it, especially at the center. And so even though this sort of resembles an eyeball, it sort of acts like one, observing everything in the middle and causing quantum particles to assume shape, to assume properties, and to create objects, or to create the reality we know. And by itself, this does sound somewhat metaphysical, and erroneously can start bringing in the idea of, for example, religion. Does that mean that this is basically God? Well, according to the scientists, it's really quite the opposite. It does not mean that the universe is conscious, or that it represents some kind of a godly being. Instead, it seems to provide an exact objective way that causes quantum states to create physical objects, relying on principles from Einstein and from quantum physics. And more importantly, potentially providing a link to both that one day could explain everything around us, assuming that this is correct. It's still very theoretical, very hypothetical even, with all of this based on our current understanding of black holes. The objects that, for all we know, could be entirely different, especially because we know that infinity does not exist, but current mathematics behind black holes involves infinity inside the black hole. This is known as the singularity. Nevertheless, this is a really intriguing explanation that essentially suggests that the coherence of the entire universe is really due to various types of radiation, for example various photons or hypothetical gravitons, coming from the edge of black holes and from the edge of the universe itself. And so if the universe was not expanding so fast, or if black holes did not exist, neither would we. That by itself is somewhat mind-blowing. But I don't think we're going to actually know much more about this other than making this an intriguing explanation to the entire universe and everything around us, until further understanding of black holes and further understanding of what actually happens right at the event horizon of these unusual objects, and what happens to things that enter black holes. That's not something we can answer anytime soon. Hello wonderful person, this is Anton, and as the title of the video suggests, today we're going to be talking about a strange liquid that seems to make electricity, using what's known as piezoelectric effect. Or is it piezoelectric? Anyway, we'll talk about the effect itself as well, because basically that's the main discovery from this recent paper that is kind of groundbreaking for one simple reason. It's the first time ever that this effect has been actually observed in any liquid ever. Which at least in theory means that we can maybe, one day, produce electricity from liquid. But in this case, a very unique type of a liquid, the one that was discovered over 100 years ago, but that still hasn't found that niche where it would be used the most. Basically, it's a discovery that still doesn't have a very good practical application, and I actually wanted to start with that. Generally, these types of liquids are referred to as ionic liquid. And by itself, this is a pretty exciting concept. A concept that's actually pretty interesting to explore because of its potential use. And so when I originally found out about this, I was super excited because I've never actually even heard about these. But what exactly is it? Well, it's basically a salt. But instead of being a crystal like the one you see right here, it's a salt that's liquid, or a liquid that possesses ionic properties. Now, pretty much any salt, including table salt, can actually become a liquid, but normally at really high temperatures. I think for salt it's like over 800 degrees Celsius. Yet some salts become liquid at much lower temperatures, and so there's actually a concept known as RTIL, room temperature ionic liquid, which represents a salt that's in the liquid state at room temperature conditions. And what makes these particular liquids different from other liquids is that they're not actually neutral. In other words, unlike water and things like gasoline, which are normally electrically neutral, ionic liquids possess some kind of a charge. And that's because inside they contain a lot of ions. And when this liquid is cooled down enough, it becomes an ionic solid, very similar to table salt. But a few decades ago, scientists realized that in certain ionic liquids, the energy of crystallization was low enough to allow them to exist in very low temperature conditions. In some cases even sub-zero conditions, going down to some pretty low temperatures in general, but in this case the actual substances were a lot more complex. But intriguingly enough, despite their discovery, and despite their unusual properties in being basically a salt but also a liquid, even decades and decades later, nobody actually found a niche yet where these liquids could be used for some sort of an important purpose. In other words, it's like a product that just doesn't have a very good use yet. But room temperature ionic liquids have even been discovered in nature. For example, when certain types of crazy ants get in a battle with fire ants, in order to protect themselves, they basically cover their own bodies with formic acid, which when mixed with acid from fire ants, ends up creating a very intriguing ionic liquid, surprisingly protecting their bodies from any damage. But that's actually the only known use in nature as of today. When it comes to more industrial use, there have been a lot of attempts to try to use these liquids for various purposes. For example, because they're not combustible and are thermally stable, previously these liquids have been proposed for electrolyte or battery use. They can also be used in nuclear fuel processing in various power plants for different types of waste recycling, or in different types of polymer processing where other liquids would not do. Or they can even be used to extract certain compounds for pharmaceutical use. But all of this so far has been hypothetical, and as of today they still have extremely limited use. Actually, one of the more exciting propositions for science was a potential use of one of these liquids for the base of a spinning liquid mirror telescope that could even be based on the moon. They would actually be really good at that. But one of the highest potentials for their use would be in solar thermal energy, for example in various solar power towers that use a unique technology in order to produce and then store energy. There's a video in the description that describes this a little bit better. And so in theory, the storage of energy in this case could be done by these unusual salts. But now, 150 years after their initial discovery, someone accidentally discovered a completely new phenomenon that these liquids contain, which in theory could make them finally useful after all. Here we're talking about piezoelectric effect, or piezoelectric effect, whatever you want to call it. The electric effect that up until now has only been seen in solids and mostly in crystals. And that's of course when you produce electric charge by applying pressure to a certain material. For example, that's the effect used in various quartz clocks, where if you actually supply electricity to a quartz crystal, it will start producing pressure and vibrating, and of course vice versa, if you were to press it, it would produce electricity. But apart from crystal watches and a lot of other smaller devices, it's even used in certain cell phone speakers, and even certain lighters like the ones we use for lighting barbecues. So despite this being a relatively small effect, it's actually widely used to either produce electricity or to use electricity to produce some kind of a deformation. But for the most part, this phenomenon has always relied on various crystals, usually containing specific ions on the inside. Yet now, the scientists have confirmed it seems to also happen in liquids, ionic liquids. And moreover, ionic liquids that can actually stay liquid at room temperatures. And like with so many other discoveries, found completely by accident when the researchers accidentally applied pressure to the cylinder containing the liquid. And they discovered that it seems to release electricity. The more pressure they applied, the more electricity it released. In the process, realizing that there seems to be some kind of a charge that builds up inside of these liquids, released suddenly when you apply pressure to all of this. Although important side note here would be, it's not a lot of charge. It's about 1/10 of what you would expect from a similar sized crystal. So in that sense, it's not super efficient. But it possesses properties that crystals do not possess. For one, being a liquid, it means that we can actually create any shape, potentially allowing us to have various designs for future batteries. It would also be a lot more environmentally friendly compared to other solid materials and can actually decompose really quickly. But furthermore, the scientists discovered that when applying pressure to these liquids, they also change other properties as well. So they don't just release electricity, they also seem to change the way that they bend the light, while changing other optical properties that can actually be used in a lot of different technologies. I'm going to assume it's going to involve lasers. Lots and lots of lasers. And though it's not entirely clear how exactly this works yet, the scientists believe that the charge builds up inside the liquid, suddenly releasing when the liquid is pressed or squeezed, with all of this restarting once the liquid settled. Confirming that essentially what the scientists discovered is the first ever liquid with piezoelectric effects. But I guess here we don't really know if this goes anywhere just yet. Since these liquids have been trying to discover their use for the past 150 years, this might be just another discovery that goes nowhere. On the other hand, because of the changes in optical properties and their overall ability to store energy, they could find some use in energy storage, especially for various renewables or even nuclear power reactors that already use various liquid salts for different types of energy storage. Or maybe it goes nowhere. It could be just a discovery that just looks cool, does something cool, leaving it as a kind of a funky experiment you can conduct by yourself, but that doesn't actually do anything very practical. Either way, still pretty awesome. Oh hey, I didn't see you there. I was admiring this beautiful earth behind me. What are we going to be talking about today? Oh yeah, another intriguing story where the press might have actually misinterpreted something that was not discovered at all. Let me show you what I'm talking about. This. It was referred to as the quantum yin and yang. With titles like Quantum Yin and Yang shows two photons being entangled in real time. Scientists visualize quantum entanglement of photons for the first time. The yin and yang of photon entanglement. And I'm pretty certain most of you have already seen this image because it went viral approximately 1 week ago. Now back then I actually had a really bad throat, which I still do by the way, so I didn't really get to make this video right away, but I was just sitting there, boiling, trying to figure out how do I actually present this because this is literally not at all what was discovered. This does not show us quantum entanglement as a yin and yang. In other words, unlike those titles, this is not an image of quantum entanglement. This is not an image of two photons entangled to each other. And honestly, this is really more on researchers in this case, because they kind of took this image without realizing that it's going to completely mislead the audience, or technically the readers, the listeners, the watchers of videos. So in some sense, this was just a pretty cool experiment with a picture that unfortunately misinterprets everything. So hello wonderful person, this is Anton. Let's talk about how this is not an image of quantum entanglement, and let's discuss what's actually here, why this is still kind of important, and to some extent what exactly is this all for. First, let's start with the technology that was actually used here and the main principles behind all of this. Or wait, first let's start with a brief 5-second introduction to quantum entanglement. In certain conditions you can create an environment where particles become entangled to one another. They start interacting in such a way where affecting one particle affects the other. And although we're not going to discuss a lot of detail, this is something that's been proven many times, one of the most interesting applications of this is with the use of photons. By splitting a laser beam, it becomes possible to entangle photons, which actually creates a lot of opportunities for different types of research. And as a matter of fact, a lot of recent discoveries in quantum physics and quantum mechanics, especially the ones involving quantum computers, would usually use these entangled photons. You can actually learn about some of them in the description below. But I guess more intriguingly, several scientists realized that you can actually use this principle to do quite a lot of intriguing things. For example, you can actually use this for encryption, or specifically sending encrypted data. So here, let's just say I'm sending you a lot of super secret data, but I'm doing this by splitting the laser beams and sending you the data along two separate streams, with each of these bits being entangled. And the thing is, if someone tries to intercept this data and tries to listen to it, it actually automatically disentangles these particles just by nature of quantum physics. It represents a kind of an observation of these particles, which means that you know exactly when you were hacked and when your data was intercepted. That's of course just one of many applications. Another application is a little bit more intriguing. You can use the entangled photons to try to scan things or to try to visualize things that would be otherwise invisible to us. For example, super tiny things, or maybe objects where there is really practically no light. Technically, this is an extension of what's known as digital holography, where we try to recreate various invisible objects by processing holograms using photons of light. And even more broadly, this is also part of tomography, with the famous example here being the MRI scan, where we try to reconstruct a three-dimensional object from a lot of two-dimensional images, creating a single object at the end. Although in digital holography, this recreation is usually done by reconstructing what's known as interferogram, an image showing us interaction or interference of light scattered by the object we're scanning. And so here we get a lot of different peaks when there is a lot of constructive interference, and we get a lot of troughs when there is a destructive interference. Here's a really good example of basically our blood cell. This is a blood erythrocyte. And this was created by looking at the interference patterns as the light interacted with this blood cell. Here's another slightly different example. This is from USGS, and this shows us the interference patterns that show us the changes in surface altitude. This is basically a radar image produced from outer space. But in the last few years, scientists have actually tried to take this a step further. They tried to figure out techniques where we could maybe use entangled photons to try to reconstruct things even faster or more precise. So in essence, taking digital holography to a completely new level. And here there's this really good video explaining pretty much all of this by David Butler. He makes these incredible classroom aids with a YouTube video in the description basically showing us everything. And here this new technique is known as ghost imaging. In essence, it's really simple. You once again take a laser, you split the beam, creating entangled photons, and then you send one of the beams toward some kind of an invisible or difficult to see object you're trying to scan, whereas the other beam goes into separate direction where there's practically nothing. And the idea here is that there is a detector on the opposite side, and the photons are supposed to arrive to this location at the same time. Now, if the two beams pass nothing, there's going to be no difference and they're going to produce no additional observations. But if the beam on the right passes through the object that you're trying to detect, it's going to become disentangled, and it's actually going to produce a kind of an interference pattern that's then going to produce the ghost image we're trying to see. Now this is ghost imaging. This is a very well-known technique and it's been used many times. But it's a relatively recent technique, so it's still being developed. Normally, to try to scan these objects, it does take quite a long time. As a matter of fact, some of the more complex three-dimensional objects could take days or even weeks of observations in order to produce the final image. Now, it usually still works, it just takes a really long time. In some sense though, this is essentially a kind of a quantum tomography. It produces the image we're trying to observe by using quantum effects. And this is a really exciting technique. It's actually going to allow us to see many different things we previously could not see. And so a lot of scientists are trying to figure out how to make this better. Which is precisely what this new study was about. They were trying to improve the ghost imaging technique. It actually even says so right here in their abstract. Paving a new route toward efficient and accurate computational ghost imaging and high-dimensional quantum information processing. And so the main achievement in this paper was basically creating this new technique for ghost imaging. A new method or a new setup that allows for exponentially faster ghost imaging requiring only minutes or sometimes even seconds instead of days. They explain how they did this in their paper, but in essence, that's pretty much it. They obviously show us some of the sample images they used, and then it just so happens that apart from other images they used, someone on the team decided to do something slightly different. Hey, wouldn't it be funny if one of the images was actually a Yin and Yang symbol? Hahaha, what could possibly go wrong? And so essentially, just like in David Butler's video where he shows us how it's possible to reconstruct a hypothetical lambda letter as a ghost image, or just like we saw right here the reconstruction of the red blood cell using a slightly less complicated setup, what we're seeing right here is literally a reconstruction of a yin and yang symbol, but obviously using that quantum ghost imaging. In other words, let me just rephrase this. It doesn't mean that this is what quantum entanglement looks like. All this shows us is a reconstruction of a yin and yang symbol using quantum entanglement. So they took a picture of yin and yang, they put it in the machine, they started their laser, fired a bunch of photons, and those photons were then able to reconstruct the image using quantum entanglement principles that you see right here. So that ghost image was basically a representation of the original yin and yang, in essence proving that their technique seems to work and works really fast. But because of, I guess, some miscommunication or maybe someone misunderstanding what this paper was about, pretty much every press release I've read so far makes this sound like this is literally the image of quantum entanglement. As a matter of fact, someone even mentioned that somewhere on TikTok, we have quite a lot of different spiritualists telling us that this is exactly what the universe was telling us all along. Quantum entanglement, yin and yang, the black and white, the hot and cold. Okay, you get the point. That's not it though. That's totally not it. This doesn't show us anything it was supposed to look like this. The image, the original image, was yin and yang. All the scientists did here was reconstruct it using imaging. So yeah, hopefully I made this a little bit more clear, and hopefully you're no longer confused about this very unusual viral story that was practically everywhere for many days. It is nevertheless still important though, because it shows us that this technique definitely works really fast, and can definitely help us advance ghost imaging techniques and even new techniques involving quantum computers. And so even though in some way this is just, I guess, quantum art, mostly showing us the visualization of the wave function, the result of the quantum entanglement, it is by no means the appearance of entanglement itself, and just shows us interference patterns between two laser beams. It is, however, still a really important achievement, because here the team found a way to potentially extremely quickly assess various entangled particles, specifically allowing us to suddenly read several properties about each particle, making this process really fast. And just to give you a little bit more physics here, normally in a much simpler setup, we're only reading one single property of the entangled particles. For example, their spin. But what if you actually wanted to read several at once? Polarization, spin, momentum, even the position. Now in this case, to read several properties, it requires a much more complex setup, and it actually takes much longer to reconstruct everything, also increasing the number of potential errors. And so by using this technique known as biphoton digital holography, it might become possible to interpret the properties of various entangled photons extremely quickly, allowing us to reconstruct everything in the process. And so in a nutshell, it just opens up a lot of doorways for possibly a really efficient quantum computing technique, or once again possibly a way to reconstruct something really difficult to see very fast. Although I guess at the moment this is still a proof of concept, so we don't really know where all of this goes just yet. And so definitely a really exciting paper and a really exciting discovery, just not for the reasons announced in most of the press releases. The quantum entanglement is not yin and yang, and this is not a discovery of some cosmic secret that was hidden from us until now. So yeah, sorry. Hello wonderful person, this is Anton, and today we're going to be discussing some new discoveries about lightning. Mostly discoveries made in the last few years, with the main focus being this paper that you can find in the description below that essentially describes a new technique scientists discovered where they can sort of redirect the lightning by using lasers. But I guess before we start all of this, I wanted to start with the obvious. Even today in 2023, we still know and understand so little about the phenomenon of lightning itself. We kind of understand the main principles, and we obviously understand that this is an electromagnetic phenomenon, and a phenomenon that involves two different charges, the one in the clouds and the one on the ground, to then create a connection between 2 points, but there are no actual explanations for pretty much most of the phenomena involved here. Even the definition itself is not really clear. We sort of think of this as lightning, but there are also additional phenomena known as sprites, or other phenomena that go the other way, known as jets, that we'll actually discuss in one of the videos you can find in the description, that are also technically lightning as well. So in a sense, this is a phenomenon that still is not really clear. The only thing that's clear about it is something that was discovered by the famous Benjamin Franklin back in the 1700s. Ben Franklin was a really smart person. And back then, along with several other individuals, he was trying to solve one major problem, figuring out the nature of lightning. What exactly was it formed by, and what was creating this unusual fire in the sky? And his hunch, along with several other people, was that it was probably electromagnetic or electric in nature. And his iconic kite experiment was essentially able to prove this in 1752. In this experiment, as you might already know, Ben Franklin and his son flew a specifically designed kite with a string made from wet hemp that would allow conductivity connected to what's known as the Leyden jar on the other end. This is an early example of what we would now refer to as a capacitor, something that's able to store electricity for later use. And so in this case, by flying a kite extremely close to a thundercloud, actually dangerously close to a thundercloud, the hemp string that became wet over time started to provide conductivity, energizing the Leyden jar in the process. And as the Leyden jar was being charged, some of the threads inside the kite string started to be repelled, indicating that electricity was involved indeed. And so after some time, when Franklin moved his hand extremely close to the jar, he observed a spark, indicating that electricity was indeed involved. Although in this case, he was never struck by lightning. As a matter of fact, had the kite been hit by lightning, it's quite likely that Ben Franklin might have not survived this at all. So in that sense, he was actually risking his life and even his son's life to perform this experiment and to determine the nature of lightning. But one of the main reasons for this experiment was to actually figure out how to protect houses or various structures from constant lightning strikes. Back in the days, several centuries ago, lightning would cause a lot of problems for a lot of people, especially for taller structures and especially for churches. Cathedrals, especially large ones, would receive a lot of lightning strikes, very often causing fatalities, or sometimes even resulting in major fires. And so one of the first propositions to try to battle this was a creation by this person, Prokop Divish, a Czech theologian and natural scientist, who constructed his Machina Meteorologica. He believed that this was actually something that would disperse lightning above a certain location. And to everyone's surprise, it did seem to work, but not for the reasons he believed, and also not the way he intended it to work. This was an accidental creation of the first lightning rod, and a few years later, Ben Franklin was able to create a much better version of this, producing a very important technology we still use today. Pretty much all major tall structures, all towers, all buildings in the world will have what we refer to as a Franklin rod somewhere on top of the structure, with the rod essentially serving as a kind of a grounding network in order for lightning to strike the top and to then propagate into the ground without affecting the rest of the building. And so in the last couple of centuries, this particular idea or technique has been perfected so much that today we don't have to worry about lightning strikes pretty much almost at all, even in airplanes, even though this was an issue several decades ago. And since something like 9 million lightning strikes occur on our planet pretty much every single day, you can imagine this used to be a pretty big problem before. But it still is today for certain types of structures. For example, when it comes to rocket launches. As a matter of fact, several lightning strikes have already previously delayed various rocket launches and even created some other problems. And in this case, you can see that there's a very sophisticated lightning protection system surrounding this launch pad at Cape Canaveral. And when it comes to rockets, or actually really anything containing liquids, even things like trees that contain water, sometimes a lightning can cause these objects to explode, which is why Franklin rods or lightning rods sometimes are just not enough. And so for some of the more sophisticated and some of the larger structures, something even more drastic has to be done. And that's pretty much where this research comes into play. The scientists were able to figure out how to divert lightning and how to actually make it move in different directions by using lasers. In this case, actually testing this not just in a lab, something that has been done previously, but by testing this on an actual mountain during a thunderstorm involving a real tower. And in this case, by using a powerful terawatt laser that would shine right above the tower in order to see if the lightning could be redirected. Here's sort of the schematic of all of this, showing us the laser and the tower itself. And so this was a pretty important and a pretty intriguing experiment. But in the process, it did show that it seems to be possible. The lightning does seem to follow the laser and can indeed be guided in a certain direction. Here are some of the pictures captured during the lightning strike, showing a part of the lightning directly following the laser light. And in this case, the scientists believe all of this happens because the laser itself ionizes the air in just the right way with the lightning then following the path created by the laser through the process of ionization. And this idea was originally theoretically proposed back in 1974, so this is actually not a new proposition. But a lot of earlier experiments, including this one from 2008 in Mexico, did not show any promising results. But in this case, the scientists realized it was maybe because they did not use the proper laser. The laser they used in this study was able to produce several thousand pulses per second, so it was actually much faster, and was obviously a lot more powerful as well, with the laser then causing some of the ionized air to create low pressure areas that the electric discharge can then follow along. And so in this case, it's most likely the speed of the laser that seems to create these effects, which actually relates to this other study you can find in the description that to some extent was able to recently explain why lightning seems to zigzag around. These tiny zigzags are produced by an excitation of oxygen that seems to remain ionized for just a fraction of a second, approximately 7 microseconds. And during this period of time, it creates a tiny channel, which then pauses for a little bit, goes into a different direction, and keeps ionizing oxygen along different paths. In this case, the scientists refer to this as a kind of a metastable oxygen, so it only remains in this state for a fraction of a second. But it looks like by using a fast enough laser, it seems that the scientists found a way to control this to some extent, and to guide some of this oxygen in a certain direction. Which actually takes me to one of the more interesting points in regards to lightning on Earth. The zigzagging shape, and even the color of lightning here, is the result of oxygen ionization in the atmosphere. And so even though we know lightning exists on Jupiter and a lot of other planets, the shape, the color, and other properties of lightning there is very likely extremely different. It's still a similar phenomenon with a similar principle of positive charge connecting to negative charge, but it probably manifests itself in a very different way, something that we currently do not understand either. But anyway, by running this campaign for several weeks from Santis mountain in northeast Switzerland, the scientists were able to successfully divert several lightning discharges away from the tip of the tower, in this case being able to capture the lightning from as far as 50 meters or 160 feet away. This was also confirmed by detecting electric fields and X-rays generated during the lightning activity. And because this telecommunication tower gets struck by lightning 100 times a year, this first demonstration using lasers was extremely important for a lot of different facilities, or a lot of expensive facilities, where Franklin rods simply are not enough. For example, this is also a pretty big issue for a lot of different airports, and so technically by using lasers, it might become possible to protect airports from a lot of lightning strikes as well. With larger and more sophisticated structures usually requiring really complex materials in order to protect structures from lightning strikes. And so this particular technology could potentially provide really important solutions. But this was just the first such experiment, first successful experiment, so it might take a while before something is officially developed. Okay, imagine going to a conference where you're about to present a really important paper. You're super excited, everything goes well, especially because your discovery rewrites our understanding of Newtonian physics. The word groundbreaking might not be even enough to describe this. And with something like 5 sigma standard of your results being correct, you now might have a chance to maybe win a Nobel Prize because you've just discovered something absolutely incredible. Everyone's super impressed, huge success for you as a researcher. Then, the next guy comes on stage and seems to have found pretty much the opposite, with even more significance. And the evidence that the new speaker presents seems to be very difficult to argue with. So yeah, what do you actually do in that case? And though this might sound fictitious, in theory this is actually exactly what's going to happen during one of the MOND conferences, where several speakers are going to be presenting the results. And so, hello wonderful person, this is Anton, and today we're going to be discussing this relatively new study that actually was not particularly popular at first until the relatively recent press release from a small Korean university sort of made it go viral, with everyone in astronomy basically talking about it. But the thing is, we're not really discussing the study itself, but the topic as a whole. Because, as you'll learn from this video, we actually have no idea who's correct in this case. But before this, let's set up what the problem actually is, and what various scientists are trying to solve. This is once again an attempt to solve the idea behind dark matter, a strange phenomenon that we know exists, but whose actual origin is kind of difficult to explain. Now, there have been so many different attempts to solve this and to try to explain it one way or another, But the main explanations today involve either some kind of a super difficult to detect particle that seems to be everywhere, and by the way, it potentially is difficult to detect because it's just extremely low in mass, or maybe something needs to be rewritten about the model we have of the universe, and maybe we actually have to rewrite the fundamental gravitational formula, actually Einsteinian formula. Maybe something is missing from Einstein's equations, and maybe something here just doesn't really work well in certain conditions around the universe. And that's despite the fact that in just the last 10 years, there have been hundreds of different attempts to actually disprove Einsteinian theories, with all so far actually failing. And this is one of the reasons we often see articles online that basically state something like, Einstein proven right again, it looks like gravity does work the way we think it works. But there could still be a chance maybe we don't really understand everything. And the most famous idea challenging Einstein and Newton is known as MOND, Modified Newtonian Dynamics. The idea that began as an explanation for galactic rotation curves, but that then started to be expanded into the rest of the universe as well, trying to explain a lot of other phenomena we observe. And the thing is, this is where it gets super complicated, because even though just modifying the formula does explain certain galactic curves in certain locations, trying to explain everything else we observe in the universe, according to MOND, would require ridiculously complex modifications and something that goes way beyond just simple invisible particle. And more importantly, the evidence was just not there. Now, there are actually several scientists out there that are strong proponents of MOND and have been trying to prove it for many decades. And the Korean scientist that wrote this recent paper seems to be one of them. But the problem is there's also quite a lot of papers challenging MOND and succeeding at pretty much disproving everything. But whether the MOND is correct or not, well, it's really not what this video is about, because here we're going to discuss a slightly bigger problem in science. Something that's actually become a huge issue in the last few years. Just for fun, I googled astronomers find, and just look at the titles here. They find a new stellar object, they find an object no one has ever seen before, they find a planet that shouldn't exist, so quite a lot of somewhat clickbaity titles. But the thing is, in most of these cases at least, the actual discoveries were somewhat real. Maybe not as groundbreaking as the title makes it sound, but still real nonetheless. But on top of this, we also had titles like this. Scientists confirm major breakthrough in nuclear fusion. New research doubles universe's age to 26.7 billion years. Harvard astronomer hunting for UFOs on the ocean floor may have found something. And of course, the biggest of them all, superconductor breakthrough could represent biggest physics discovery of lifetime. Huge claims that were either disproven almost right away, like with the LK99 superconductor, or claims that are going to be eventually disproven with time. Although for that fusion claim, it's really more of a representation of what it's actually for. I mean, we're talking about a weapons research facility, not something that's trying to create clean energy. But anyway, the main concern here is that the sensationalism in science has actually reached a completely new level of absurdity. We've reached a point where it's very difficult to tell what's real and what's not. Which is actually ironic, because in the last couple of years, I realized that several science communication channels, including technically I guess myself, have now started to slowly become debunkers, not really presenters of new discoveries. I mean, I've watched quite a few videos from Joe Scott, for example, who now has several videos where he basically challenges all of this. Same thing with Kyle Hill, and even more so with channels like Professor Dave Explains. And that's really because of all of these unusual claims coming from everywhere. And so when I see an article like this with the title, Smoking Gun Evidence for Modified Gravity at Low Accelerations from Gaia Observations of White Binary Stars, one of the most reshared articles in the last couple of weeks, it sort of makes me go, huh? What? What exactly are they talking about? And why is it that I think this is maybe not really exactly true? And the reason I'm saying this is because right before I read this article, a couple of months back and even 3 months back, I read separate articles that seem to actually basically state the opposite. And so I guess the question is, so how exactly should we approach these articles, and who do we basically believe? Well, the obvious answer for scientists would be, time will tell. I mean, obviously, as Carl Sagan said many times, science is not just the body of knowledge, it's a way of thinking. Here you actually wait for results, confirmations, and maybe further studies, or even meta-studies, trying to actually find out what's going on. But if you just want to read one article, and if you don't want to bother with the whole scientific process, what do you do then? That's right, you subscribe to this channel, that's what you do. Okay, on a more serious note, well basically here what I would do is ask a simple question. How exactly did scientists come up with all of these conclusions, and is there any chance that maybe they miscalculated something, or maybe used data that's not really good? And so here, let's actually talk about the articles first and discuss the potential conclusions. And so first of all articles I'm going to be discussing were actually based on pretty much the same data, to some extent. And here we're talking about some of the most incredible data coming from the iconic Gaia telescope. This is basically as good as it gets when it comes to observations from our own galaxy. Now, Gaia telescope is really good at detecting motion of various stars across the night skies and has now actually released data 3 separate times. The most recent release from July of 2022 revealed so much new data that we can now actually start making relatively accurate calculations and predictions, even involving stars that generally do not look like they're moving much. And that actually includes binary stars, or even multiple star systems that generally do not move at very high velocities, but whose motion can now be detected with Gaia. And the thing is, apart from galactic curve motion, in the past both MOND and a lot of other theories proposed that we can actually use binary stars as potential evidence for some kind of an unusual gravitational effect when it comes to modern understanding of gravity. Although here we're not really talking about binary systems where stars are relatively close to one another. We're actually talking about what's known as wide binaries, binary systems where the stars can be separated by up to several thousand astronomical units, with a single orbit potentially taking thousands of years. And according to MOND, for example, it's actually in these systems that we can now start detecting variations in terms of the orbital motion that's going to be different from what's expected from either Einsteinian or Newtonian gravity. The actual math in here is pretty well understood, and so it becomes a matter of getting evidence and trying to match the evidence with observations. And so, for example, for our own solar system, we should actually start seeing various effects predicted by this idea at a distance of about 7,000 astronomical units. Obviously, we haven't found anything at these distances in the solar system just yet. But by looking at various other systems from a distance, it might become possible if we actually collect data for hundreds, thousands, or even millions of stars. And that's of course where the data from Gaia comes in. It was able to collect quite a lot of data from various binary systems, data that's publicly available for anyone, to start making first conclusions. But the intriguing part, of course, is what these 3 papers seem to claim. The Korean paper claims a huge evidence toward modified Newtonian dynamics using a sample of about 26,000 wide binaries, and also claiming relatively high significance, basically implying that it is most likely correct. But in this case, many of the binaries selected by the authors seem to have stars with very far away distances, up to 30,000 astronomical units. But also some stars that have a relatively short separation, technically not really being wide binaries either. Likewise, a lot of the stars here are not true binaries. Some are triple stars, some are quadruple stars. And by itself this actually represents a kind of a strange sampling. I mean, I'm not saying it's cherry-picked, but it does seem to be a little bit unusual. And then we have this paper that also came out just a few months ago that pretty much used a very similar data available to everyone. Here they used an even bigger sample of 73,000 candidates, with all of the candidates selected using a relatively robust system, with every star basically being a binary, and a very specific type of a wide binary that was meant specifically for testing the idea behind MOND. And so the 2 scientists from the Queen Mary University of London relied on a much more robust analysis and discovered literally the opposite. And not just the opposite, they also have more significance. Here it's 16 sigma, essentially proving that Newtonian-like gravity seems to be correct, whereas MOND seems to be completely incorrect. And this is not even the first time the scientists behind the study tried to do this. Last time they have a bit of a mixed result, but they also used much older data. With the new analysis and the new data, this study makes a really strong case against modified gravity. But to make things even more complicated, we have a third study, once again using data from Gaia, and once again using a relatively similar analysis. Although once again here, the star selection is slightly different. And here the study seems to discover something in between. It discovers that a lot of predictions from MOND are incorrect, but it also discovers some kind of a non-Newtonian low acceleration that implies we need to re-examine certain ideas and certain theories when it comes to gravitational studies. So we have at least 3 studies with somewhat polar results. One proving something, one disproving something, and one telling the other 2 studies that they're basically both wrong. All 3 studies relying on the same data from the Gaia telescope, but of course choosing slightly different stars or basically sampling things a little bit differently. And though this particular study that discovers no violation of Newtonian physics seems to have the most robust sampling, the reality here is that we actually still have no idea what's going on. Honestly, none of these studies prove anything or disprove anything, for one simple reason. Even though we can actually calculate the motion of stars relatively accurately, it's not the same for binary systems. When it comes to binary systems, the velocity of these stars around each other is ridiculously low. Here we're talking about velocities as low as nanometers per second, and orbits that can be in different inclinations, different orientations, and of course not entirely circular. So there's just too much unpredictability and way too many factors. Likewise, as I mentioned, some of these objects are not true binaries and are actually multiple star systems where things move differently as well. Some of these systems might be falling apart, some of them might have stars nearby influencing everything, and the biggest issue of course, some of them might just need to be observed much longer in order to establish true velocities around the galaxy. And so even though by itself Gaia is able to detect velocities pretty accurately, when it comes to wide binaries, you actually have to observe things much longer in order to find the exact velocity. It's basically kind of like why we don't really know exact velocities for a lot of different objects at the outskirts of the solar system. We normally have to look at objects for several months or even several years before we can find their exact orbit. Something similar is happening here. Here we have a preliminary observation with a pretty high confidence that we did discover different binaries, but we don't really have high confidence for the exact velocity of the orbital speeds for each of these stars. Which means that these types of claims are actually wrong. There's maybe some preliminary evidence for something going on here, but definitely no smoking gun evidence for anything extraordinary just yet. Especially because papers like this, with better sampling and even better analysis, literally have the opposite result. And so at the moment there's just not enough data. It might take at least a few more releases from Gaia, possibly 4 to maybe even 6 years, before we actually have enough data to start making some preliminary conclusions about this, but at the moment this is not enough. As a matter of fact, ultimately you want to observe these stars for at least 100 years or so to actually detect direct orbital motion. We don't have anything like this yet. But because everything today is about sensationalism, and because today being a rebel is kind of cool, and we do want to prove long-standing theories wrong, it's studies like this that tend to go viral, and studies like this that tend to basically disappear into obscurity. Although for all we know, maybe it's that third study that's actually onto something. Maybe there is something going on with the gravity we don't understand, or maybe Gaia has some kind of a fundamental error in it, unable to make extremely accurate measurements of certain objects. So yeah, there's really no answer. I'm really sorry to end on this, but at the moment it's basically impossible to make any conclusions about anything. We obviously want to solve this whole dark matter mystery, and we want to find a conclusion that makes sense for everyone, but based on these papers, it's impossible to make any specific conclusion that will definitively tell us what's going on. Here I can only make one assumption. They're all maybe kind of wrong, or at least to some extent. And so only maybe in about 10 years from now, when we get even more data from Gaia, we might finally have some closure on this and figure out what's happening, or how exactly some of these scientists came up with these particular results. For now though, I'm just gonna end it on this. I have no idea what's going on, nobody knows what's going on, and sensationalism in science needs to kind of stop, because unfortunately it results in people then distrusting science long term, and that's not cool. You should trust science. It's the way of life. Okay, this one is kinda cool. In the last few months, there's actually been quite a lot of different announcements about potential discoveries related to quantum physics, potential quantum computing breakthroughs, and even various experiments that essentially try to use quantum effects to test unusual ideas, such as, for example, if we live in the multiverse. We've briefly discussed one of these experiments in one of the videos in the description. But one of the potentially most groundbreaking papers released in the last few weeks, or technically even in the last year, is really the paper we're discussing today. An unusual proof of concept that, at least in theory, has the potential to redefine how we produce energy on the planet. The concept of a quantum engine, or I guess a quantum motor. Using quantum effects in a very similar way to how we use, for example, fossil fuels, in order to drive a piston to then produce work. And though it might sound kind of far-fetched, this is exactly what the scientists behind this paper were recently able to demonstrate by producing a quantum engine using a fermion-boson crossover. A relatively complex concept that does become a little bit easier to understand once we compare this to a typical mechanical engine. And so, hello wonderful person, this is Anton. Let's discuss this new study, let's actually talk about this proof of concept, and obviously talk about why this is kind of exciting. But I guess first let's start with the symbology of what was actually achieved here and how it compares to a typical engine. Now, in a classical engine, we normally use heat to increase the pressure on the inside and to then generate work. And all of the work is produced by driving the piston. But there are obviously other physical effects we can use to try to generate similar compression and to then generate work in a very different way. Okay, let's switch gears a little bit and talk about particles when they reach extremely cold conditions. Now, in our classical world, basically the world we live in, that's relatively warm and relatively hot, pretty much everything around us is what's known as a fermion. A particle that can be either elementary, such as electron, or composite, such as various molecules, that in essence obey a slightly different set of physical laws. Most importantly, they obey what's known as the Pauli exclusion principle, a law of physics proposed by Wolfgang Pauli that basically states that various fermions cannot actually occupy the same quantum mechanical state if they're present in the same location. It obviously might sound kind of complicated, but the easiest way of imagining this is basically anything around you. A lot of atoms around us will usually have to find their own place and cannot actually be in the same location at the same time. Although in this particular case, a much better example comes from astronomy, and specifically white dwarfs. White dwarfs are a perfect example of Pauli exclusion principle. Here, inside of the white dwarf, is a bunch of electrons. These are all fermions. And they all have to be in a separate location containing slightly different energy and cannot be all in the same place. Which is essentially why white dwarfs assume the smallest configuration possible, but still have a certain size. A typical white dwarf is usually around the same size as planet Earth. And so quite a lot of different particles will also be fermions and will also be obeying the same laws. But certain particles can sometimes switch. Or in some cases they don't even have to switch because by default they will be bosons, not fermions. So for example, photons, particles of light, are the most typical example of bosons. And they don't have to obey the same laws, and specifically don't have to obey the Pauli exclusion principle. They can be in the same place at the same time and be in exactly the same energy state as well. And because photons are known to be bosons, that's why you can put a bunch of them in exactly the same place and create something like a laser. The only reason lasers exist is because bosons can basically exist in the same place at the same time and do not obey Pauli exclusion principle. But there are actually some other extreme examples of bosons, even with stuff that we're kind of familiar with. So for example, helium. Helium, like so many other things, has different isotopes. And with helium, things get really complicated really quick. For example, helium-4, one of the isotopes of helium, once it becomes cool enough, automatically becomes a superfluid. And that's because it is a boson. In this case, it starts to acquire a lot of quantum effects, and the liquid helium-4 in this case completely ignores classical physics. What you're actually looking at here is helium liquid creeping up the wall of this cup and coming to the outside, basically ignoring the idea of gravity or even the idea of friction. Likewise, because it's a boson, it can easily assume the same energy state, and you can basically condense a bunch of these helium-4 atoms into the tiniest spot possible. You can condense them as much as you want, and they're not going to mind anything. They do obey their own laws. Anyway, this might have been kind of complicated, but the only thing you have to get out of this is that there are two types of particles. There are fermions that we're all familiar with, the stuff that doesn't like to be in the same place at the same time, and there are bosons, which obey their own laws, and essentially can be seen as these quantum liquids or quantum gases that can easily exist in the same place at the same time. And while, to some extent, because of this unusual difference, maybe there's a way to use this idea to somehow generate similar effects, similar pressure, and the motion of piston, by basically using these quantum differences. And it turns out that it wasn't actually possible until relatively recently. Now though, scientists have learned to manipulate different atoms in such a way that they can actually easily convert a boson into a fermion and vice versa. And they can actually do so by changing just a few things here and there, because certain atoms don't actually mind converting from one to another, just depending on the conditions and depending on the situation. Which is exactly what the scientists have recently been able to demonstrate. So for example, just like with the helium-4 atom that can change into a boson in very cold conditions, quite a lot of other atoms do the same. And lithium turns out to be one of the elements that contains an isotope with very intriguing properties, lithium-6. It's quite abundant in nature, but obviously in normal conditions acts like a typical fermion. And interestingly, if you cool it down enough, and here we're talking about very close to the absolute zero, it essentially forms an unusual liquid-like state, sometimes referred to as the Fermi sea, or Fermi liquid. It's still basically a kind of a classical liquid, but it does contain some intriguing properties. This is what you usually get when you cool down a fermion to the lowest possible level. It's at its lowest energy. But if you start applying certain things to this liquid, things start to transition into something else. Specifically, if you start changing the magnetic field, increasing it just a little bit, the atoms on the inside will transition into something entirely different. They will now start changing into a quantum gas. Or basically they'll transform into what's known as Bose-Einstein condensate, an entirely quantum substance that no longer obeys the laws of fermions and obeys the laws of bosons. Which in essence means that by changing the magnetic field just enough, it becomes possible to transition lithium-6 atoms in between boson and fermion states. Although in this case, they also trapped all of this with a laser whose power was changed just a little bit, and so it was basically a combination of magnetic field and the interaction with the laser. But in essence, what this creates is literally a 4-step process. A compression step, this is when the piston closes, a fermion step, equivalent to ignition in a typical engine, an expansion step, equivalent to pushing a piston out, and a boson state that resets everything to the original location. But obviously, instead of using heat like in a typical engine, here they basically used quantum effects. By shifting the magnetic field and the laser just a little bit, it transformed the lithium-6 from a fermion to a boson, back to fermion, back to boson. And because bosons and fermions exist in a different state of energy, with fermions obviously creating much more pressure than bosons, to some extent it creates a very similar effect to driving a piston. When the lithium becomes fermionic, it creates more pressure. When lithium changes to bosons, it reduces pressure. In theory, this would be enough to drive the piston. And hypothetically, this is exactly what the scientists were able to achieve in this first experiment. They didn't have an actual piston just yet, but by using the optical and the magnetic trap, they were able to achieve approximately 1 million vibrations per cycle with approximate efficiency of 25%. Although here it's important to note that even more energy was required in order to cool everything down and in order to use the laser. Nevertheless though, the proof of concept was definitely successful. Here the engine was run by using nothing except for energy difference associated with quantum matter at very cold temperatures. And so by changing things from fermions to bosons over and over, it essentially created the necessary pressure differences. But this is obviously still far from being a practical engine. And obviously it's also something that only works in extremely cold conditions in very specific lab environments. And so obviously this is not something we're going to be able to run our cars on, but it's maybe something we can use for a lot of advanced technologies, including one day, maybe, quantum computers. But exactly what this leads to is still too early to tell. This is still just a very first proof of concept, and there's really no way to miniaturize this to make this more efficient just yet, and it technically doesn't even have any practical application for anything. I mean, in theory, if we do find the right conditions and the right place to use this, it could definitely generate unlimited energy by just using these very unusual quantum effects. But I guess in some sense, this particular invention is maybe just a little bit ahead of its time. Quantum computing is still in its infancy, and we don't even know if it ever is going to pick up. And for a lot of other quantum technologies, the actual benefits coming from this are maybe not really that useful. But if one day we finally develop what's known as a quantum battery, this is definitely one way we can easily charge these batteries in order to run the entire system. So yeah, definitely technology of the future, not the technology we're going to be using anytime soon. Hello wonderful person, this is Anton, and today we're going to be discussing some really intriguing discoveries in regards to the very famous experiment involving light. The double slit experiment that to some extent you see right here. Although in this case, for the first time ever, instead of producing the typical pattern that is usually observed when light passes through two different tiny slits, creating the famous interference pattern that you see right here and that we're going to discuss in a few seconds, the scientists were able to create something entirely different, an interference pattern in time, not in space. Which obviously sounds kinda cool, sort of mind-blowing, but also needs to be explored a little bit more. But before we talk about the actual discovery that you can find in the description below, let's briefly discuss this experiment and its main purpose. The experiment that was originally conducted by the British Thomas Young in order to prove something that the scientists were kind of arguing about back in the days. Is light a particle or a wave? And by using this particular experiment, he was essentially able to produce the interference pattern that's sort of expected from a typical wave, thus kind of confirming the light's wave-like nature. Something that was generally accepted for a pretty long time until Einstein came along and basically said, oh yeah, by the way, it's kind of both. It's a wave and a particle. And that sort of blew everyone's mind, but that's a different story for another day. Because it turns out these patterns are also produced by pretty much anything involving any kind of a particle. It does not have to be light. You can also produce these by, for example, using electrons, using atoms, or even using certain molecules. As a matter of fact, one of the larger single-atom molecules out there, Buckminster fullerene, also known as a buckyball, that basically contains 60 different carbons, was shown to produce a very similar pattern as far back as 1999, with the experiment then repeated several times, resulting in these beautiful interference patterns you see right here. This image was even used as a cover page for one of the issues of Nature Nanotechnology magazines. So basically, particles can be waves, waves can be particles, and you can sort of create the interference pattern because according to quantum mechanics, very tiny things will usually have a kind of a probability of existence in a certain location instead of an actual position that you can know for sure. But it looks like after 220 years since the original demonstration by Thomas Young, the scientists discovered something else really unusual and really unexpected about certain types of light passing through certain types of slits. In this new paper that you can find in the description below, they created a very similar pattern that seems to also occur in time. But in this case, instead of changing the actual shape or producing waves with various peaks or various locations where things cancel out, creating the brighter and darker fringes, they were able to create something similar where instead it's the frequency or the color that changes, but changes in time, not in space. But in order to create this pattern or this interference, they essentially had to come up with what the scientists refer to as time slits. And so instead of two physical holes or two physical slits, these would be slits adjusted in time in order to change the reflectivity of material. Material known as indium tin oxide, found in a lot of different phone screens, that's able to change its reflectivity from being transparent to reflective when interacting with certain types of light, which basically allow them to create a way for the light to pass in certain conditions and a way for the light to be reflected in other conditions. But in this case, the change in reflectivity is not instant. It takes a tiny fraction of a second, specifically 10 femtoseconds, which essentially creates a time slit with a permanent frequency that then starts affecting the light itself. And so by shining a kind of a laser pump to produce these time slits, this allowed certain other types of light to go through, but only during certain time. But by then using a second pump laser, it started to create these unusual interference patterns as if light was passing through two spatial double slits, but instead of changing the shape, it was changing frequencies. Here's maybe one way of trying to visualize this, where we have the spatial slits producing the interference in space, and the temporal slits producing the interference in time. And I know it's kind of difficult to maybe imagine this, so maybe let's try again. In the original experiment, what changed was the angle at which the light comes out from the slits, with waves then interfering with each other, creating certain locations where the waves were much brighter, producing much more luminosity. But in this new experiment, instead of changing direction, the light changes frequency, essentially creating a variety of color inside a single beam of light. And so the brightness stays the same, the amplitude doesn't change, but the frequency or the color does. Which is sort of mind-blowing when you actually think about it. I mean, at this point it would be really fun to see if someone can actually combine both experiments to produce a kind of a shift in both time and space, and to maybe create some kind of a very beautiful prism-like effect, but the effect that would be kind of similar to the interference pattern produced by regular double-slit experiments. But one of the reasons that scientists believe it's even possible in this case is because of the unusually fast response time of this very strange material used in smartphones. It was apparently 10 to maybe even 100 times as fast as expected, allowing it to shift from reflective to transparent in just 10 femtoseconds. A really small unit of time. And so because of this really high speed of change from reflectivity to transparency, it was able to produce the beautiful pattern the scientists observed. But the scientists are still not entirely clear why it's able to do it so fast, even compared to modern theories. Which basically means that not all materials are going to be able to produce this unusual pattern, but which also means that we might have discovered a completely new phenomenon that one day could find use in a lot of groundbreaking technology. For example, it could one day be used as a kind of a memory for a lot of laser-based quantum computers, or to produce various metamaterials where control of light through both space and time is required. Some scientists even suggested that it might take us a little bit closer to recreating actual human brain, in essence allowing us to recreate neuromorphic computing that happens inside the brain itself. While at the same time this can also be a perfect material to start demonstrations on various time reflections and another concept known as time crystals. The concept that you can learn more about in the description below, which was originally proposed by Frank Wilczek back in 2012, describing a time-based analog to a typical crystal, where the orderly arrangement of atoms doesn't just happen in space, it also happens in time. Something that might be important for example, quantum computing. One day it might become a kind of a quantum computer memory. Although that video in the description describes this concept a little bit better. This has already been shown by several different experiments to be real and can even be produced in various quantum computers. But by combining this concept with the time-based interference pattern, the future studies might actually discover some other absolutely ridiculous phenomena nobody can even imagine right now. So technically this is one of the more intriguing and potentially more groundbreaking discoveries in the last few years. But exactly where this leads just yet, nobody knows. Hypothetically speaking, can the universe just kind of end? One day it's there, the other day it's not. And though common sense kind of tells us that, yeah, no, that's not gonna happen, quantum physics tells us otherwise. As a matter of fact, there is a non-zero chance that one day the universe does actually just completely end for no reason whatsoever. For pretty much the same reasons why it began. Today, modern cosmology establishes that, for the most part, it's quite likely that the universe just kind of began out of nothing, probably as a result of some kind of a quantum fluctuation. And so, why can't it just end the same way? And though this idea might sound a little bit presumptuous and potentially too hypothetical, there is a physical explanation referred to as the false vacuum decay that actually does propose that it is possible, though extremely unlikely. And so, hello wonderful person, this is Anton. Today we're going to discuss false vacuum decay. And not just a hypothetical proposition, but holy cow, an actual physical experiment that was able, for the first time ever, to reproduce a kind of a model for the false vacuum decay, technically proving that, yeah, it is actually possible. As in, it's possible, quantum mechanically, for things to undergo this unusual phenomenon and thus enter a new state. But it doesn't mean that the universe is going to end anytime soon. And so let's discuss this particular study and this experiment, more importantly discuss this proposition and what it means, and in the process, learn a little bit more about quantum mechanics. And here I guess let's start with the basics. Even though in classical physics we understand vacuum as completely empty space, today based on quantum experiments we know that this is not true. Empty space is really not that empty. It contains what the scientists now refer to as quantum foam, an idea from the quantum field theory that represents a kind of a false vacuum. But I think this animation by Derek Lineweber basically represents it the best. Quantum foam in this case basically shows us that empty space is really not that empty. Vacuum has energy and is produced through appearance and disappearance of various virtual particles that appear for a moment and then self-annihilate into nothingness. And to some extent this has been proven with various experiments, such as the experiments showing the Casimir effect. Basically, by placing two plates close to each other, even if there is nothing in between them, there's actually going to be pressure from the outside because the quantum foam inside produces less particles than the quantum foam on the outside, thus producing pressure that should not technically exist in classical physics, which in essence once again highlights that the universe, even if there's complete vacuum, will still contain some kind of a minuscule energy. And today this vacuum energy is also known as the lowest possible energy state in the entire universe. But the thing is, in a lot of different quantum theories, it's not believed to be the lowest state, because technically, you could maybe remove all of these quantum fluctuations and this quantum foam, reaching an even lower state of energy, or what the scientists refer to as the true vacuum state. And so here we have this very unique proposition. Maybe, just maybe, it's possible for the universe to go from this to something more like this. A much lower energy state and potentially even the lowest level possible. And so sometimes researchers refer to this as a metastable state, or basically not permanently stable state, whereas this is the stable state. Now it's not entirely clear how and why such an event would occur, but in quantum physics it does seem to be possible. In other words, it's a state where all of this quantum foam becomes very silent, very quiet, and non-existent. And the way this might happen is through the process known as bubble nucleation, or a sudden formation of a bubble with zero energy inside that then suddenly starts spreading throughout the entire universe. And so here we have this tiny bubble forming somewhere in the universe, and then suddenly growing larger and larger, pretty much at the speed of light, eventually covering the whole universe, and making the entire universe transform into a completely new state, a lower state of energy. But we have no idea what exactly this would mean. Maybe this will just change a few properties of the universe, maybe it will make the universe grow much larger, or maybe it will destroy everything. So there's no clear answer about what's going to happen. But if our universe is truly in this false vacuum state right now, then reaching that true vacuum state is definitely something that could happen. And intriguingly enough, if it does happen, we're not even going to know. Even if it destroys the universe, all of this is going to happen suddenly, instantly, and at the speed of light. One day you're there walking your dog, and then just like that, in an instant, everything is gone. Sometimes it's compared to some kind of a sinkhole that suddenly swallows everything around it. But in order for this to happen, there has to be a way to build these bubbles. Something has to be able to create them one way or another. And researchers studying these bubbles always propose that it has to be a result of some kind of a quantum tunneling, or basically the same quantum effects that produce quantum foam may occasionally reach that zero point, suddenly creating a total energy zero bubble that then starts to spread. But all of this up to this point was more or less somewhat theoretical and very hypothetical. Just something you find in physics books, or something theoretical physicists basically tell their friends at the dinner table for funsies. And that's until this recent study that to some extent created a model that actually recreated this. First experimental evidence for false vacuum decay. Although in this case they obviously did not use the universe itself. They did use a gas, but a very cold gas almost at absolute zero that acquired a lot of quantum effects extremely similar to what we usually observe, or to what we usually expect, from anything at these very low temperatures. And so basically here the gas acquired a lot of quantum properties. But interestingly, at some point, through a carefully controlled experiment, the researchers were able to produce a tiny bubble that then started to spread. And as it spread more and more, the entire gas state reached a much lower state of energy, or the so-called true vacuum. Or in other words, they were able to recreate these vacuum bubbles, thus kind of proving that false vacuum decay is maybe somewhat possible. Or at least a phenomenon that definitely exists in physical systems. And more importantly, in this case, these bubbles resulted from being activated through the introduction of a little bit more energy. In this case referred to as the thermal activation. And for a lot of cosmologists and a lot of theoretical physicists, this would be a really important study. Because vacuum decay plays a really important role in a lot of different ideas. For example, the creation of the universe itself. The formation of space-time and the formation of matter is actually believed to be the result of a kind of a transition state very similar to a false vacuum decay. Or in other words, the universe had nothing at first, then suddenly had stuff in it. And all of this can be explained using these ideas. As a matter of fact, even the Big Bang theory can also be explained this way as well. And even more exotic ideas such as the inflation theory can really only be explained as a result of this false vacuum decay into a different energy state such as the one we have today. And so in other words, one of the main explanations we have for this unusual expansion of the universe in the beginning, where basically the universe suddenly became much larger than it used to be at first, that's what the cosmologists refer to as the inflation, is basically a result of this false vacuum decay. It's quite possible that after the Big Bang, the universe had much higher energy. Then suddenly, a quantum bubble suddenly makes everything collapse into a lower energy state, which might have resulted in a sudden expansion of everything around us. And so the inflation itself has been previously explained as a result of the Higgs field being trapped inside the false vacuum state. In other words, this unusual phenomenon could potentially explain pretty much everything that was always confusing about the entire universe. How the universe began, how it changed so dramatically in the first few seconds, why it's still changing even today, and even what might eventually happen later on. And since this particular experiment physically proves that this is a phenomenon that does exist, this experiment essentially created a very important analog for the early universe itself in order to help us understand what might have happened. But it obviously does not answer the question of what would happen to the universe if it reached an even lower energy state. mostly because we have no idea how the physics around us would change as well. We don't really know if this is going to be a sinkhole that swallows everything, with the entire universe basically disappearing or transitioning into something that can no longer support matter, or if it's just going to change into something slightly different, just like it did during inflation. Either way, the results from the study are still quite intriguing. They definitely confirm that it's possible to exist in a metastable state for a long time, until something creates a bubble that suddenly transforms everything into true vacuum. But how exactly such a bubble would form in the real universe is not something anyone can answer right now, or if it's possible at all. Nevertheless, as I mentioned, a lot of physicists do believe that there is a non-zero chance that it is possible, and that one day the universe might change after all. But in order for this to happen, it's quite likely that the universe has to find itself in a place with no gravity. Or basically, current explanations suggest that in order to build this bubble of total energy zero, it has to be created somewhere where there is no gravitation whatsoever. Because gravity seems to distort vacuum energy and prevents these bubbles from forming by not allowing them to get big enough in terms of volume and surface ratio. Which means that, I guess, for as long as there is matter in the universe, maybe it won't happen at all. But on the other hand, other papers have actually proposed that it might form in certain extreme conditions, such as for example when two black holes collide, producing tiny bubbles right in between them, milliseconds before the collision. But because these environments are so hectic and because they only last for a millisecond, and also because there's so much other energy including potentially Hawking radiation, these bubbles very likely disappear as soon as black holes collide. In other words, in terms of theories, there are definitely a lot of propositions when it comes to this true vacuum, or these true vacuum bubbles. But at least in terms of the universe itself, we still have no evidence from anywhere. For now, we just have this evidence by using an analog environment using ferromagnetic gas at extremely cold temperatures. Something you can learn more about in the study in the description. But with future similar experiments, we might actually get more answers about what's going to happen to the universe, or what happened to the universe in the beginning, and how it transformed from one state to another, leading to all the phenomenon we have today. So definitely a kind of an exciting study, and something that I hope someone recreates, learning more details in the process. Oh, that looks like a pretty good thumbnail. Hello wonderful person, this is Anton, and today we're going to be discussing this relatively intriguing new research on the idea of quantum teleportation of energy. Or to phrase this in much simpler terms, being able to create energy in a completely different location out of what seems to be nothing. And even though in modern physics the idea of creation of energy out of nothing usually is met with a lot of skepticism and normally a lot of laughter, things change just a little bit once you start introducing ideas from the quantum physics, and specifically the concept of quantum vacuum state. Something that various experiments have been able to prove for a very long time now, producing various energy fluctuations in what seems to be complete vacuum where there should be nothing there. The principle sometimes referred to as the quantum fluctuations. And so in this video we're going to discuss some of these new discoveries, some of these new propositions, and the two experiments, very recent experiments, that kind of made this possible. Made what possible? They sort of showed that it might be possible to transfer energy remotely through the process of quantum teleportation, and thus, in theory, produce energy out of nothing in one location, but with a small caveat. This energy has to be produced elsewhere. And so let's briefly discuss the theory behind this, because at first when I read this, I was a bit skeptical, but as I kept discovering more and more, I realized that the scientists are actually onto something here after all. With this most recent experiment, conducted in January of 2023, once again confirming that it seemed to be sort of possible. But here the theory is super important, because conceptual misunderstanding of this topic is very common. First of all, despite the name, this is not Star Trek-like teleportation. It doesn't involve any wormholes, it doesn't involve any portals, it does not involve traveling faster than the speed of light, and does not violate any physics. As a matter of fact, the word teleportation is maybe even not the best word to use here. But it does involve quantum ideas, such as entanglement, which then starts producing various effects across various distances. But I think the easiest way to understand what's happening here is to actually kind of go through the same questions the original scientist was going through when he sort of proposed this. It was this Japanese scientist that you see right here, Masahiro Hotta, seen here pictured with Stephen Hawking. And his reasoning was really simple. Well, the scientists have been confirming these quantum fluctuations. or basically fluctuations in the quantum field itself that produces tiny minute variations of energy, with particles appearing and disappearing, and even the vacuum itself producing a kind of a jitter. At the same time, other experiments have definitively shown that you can actually transfer information from one location to another if two particles are entangled. Or basically taking one particle entangled to another particle, or taking one photon entangled to another photon, can easily allow the scientists to transfer information by affecting one of these particles and seeing the changes on the other side almost instantly. And so using this logic and understanding that these energy fields exist everywhere in the universe, Dr. Hota made a really simple assumption. Shouldn't it be possible to transfer energy remotely using very similar principles? Which intriguingly also led him to various ideas about negative energy. Something that some scientists believe might be happening around black holes. As black holes shrink and as they evaporate using Hawking radiation, this can also be actually seen as a radiation emitted from their interiors as they swallow negative energy. Which by the way relates to another video about this topic that you can find in the description below. But besides black holes and besides negative energy, his ideas started to connect several major topics: entanglement, negative energy, and teleportation of energy across distances. Although ironically, as it usually starts in many cases, he was initially trying to sort of disprove this. But as he kept digging more and more, he kept discovering things that seemed to support his original hypothesis. It may be possible to create some kind of a negative energy inside quantum vacuum, making it give up energy that did not exist there before. It might be possible to produce energy out of completely empty vacuum. But with a very important side note, this energy has to be coming from somewhere else in the universe. It just doesn't have to be in the exactly same location in the same vicinity. And so to some extent he laid foundations, theoretical foundations, for the main principle of quantum energy teleportation. But not like zapping electricity across the entire universe or trying to create massive amounts of energy elsewhere by using nothing. We're actually talking about something on much smaller scale. One good example here would be atoms, changing the energy level inside the atom from the ground state to the slightly more excited state. And in this case, two atoms would have to be entangled. And even though most of this was kind of theoretical and even debatable for over a decade, in 2022 there was a major breakthrough with at least one experiment you can find in the description below. In this case using principles of magnetic resonance, the same principles that allow us to use MRI machines. And so here by using magnetic fields, it becomes possible to manipulate various quantum states inside various atoms. And for this first experiment, the scientists relied on carbon atoms that were previously entangled inside a tiny microchip. And so here, just like in previous experiments, by changing any information inside one atom, the information inside the other atom would change as well. But the scientists decided to focus on changing the energy of one atom. And they did so by using very specific radio waves, which basically changes the ground state around the atom itself. But when they did this in one atom, this also affected the entangled atom located slightly farther away. Although because these atoms were entangled, and because the information transfer had to happen as well, none of this violated any laws and nothing here traveled faster than light. And intriguingly, just like the hypothesis predicted, the entangled atom changed its energy in the opposite direction. And so it wasn't just the information transfer, it was also energy transfer. But because this was true entanglement, nothing here violated any physics. The information and energy transfer still happened at the speed of light, but it happened much faster than it would have happened if this involved any actual physical transfer. Even though normally this would take approximately a full second for the energy of one molecule to transfer to the other molecule, during the experiment this only took 37 milliseconds, or about 20 times faster. So kind of showing that this was teleportation after all. Just teleportation following the laws of physics. And having conducted this several times, the scientists confirmed that there was a correlation between the increase of energy on one side and the decrease of energy on the other side, as if one side was being charged and the other side was being discharged. And now, almost a year later, we have another proof, but this time using a quantum computer. In other words, the scientists were also able to create this by using a publicly available data from the IBM quantum computer and by creating an algorithm that would then transfer the energy from one location to another inside the quantum computer as well. And so essentially, by combining the entangled particles with the transfer of classical information, once again the scientists observed that on one side there was an energy increase, on the other side there was and energy decrease. So kind of like negative energy. And it's really this observation of negative energy that's one of the more significant discoveries coming out of these studies. And because the original hypothesis also connects this to black holes, this could eventually lead to some major discoveries, including maybe some clarifications of quantum gravity theories, or basically the theory of everything. And one of the reasons this is now physically possible is really because of advances like this. This is the IBM Q System 1, one of the earlier quantum computers. And not so long ago, I guess a few years ago, IBM made all of this easily accessible through a relatively easy to use web application that then allows you to remotely program and control certain operations on a quantum computer, basically allowing the scientists to conduct these experiments without ever leaving their house. Although in this case, the teleportation itself only happened inside a tiny computer chip. So in order to confirm all of this has to be now done over much larger distances. For example, maybe using the network in the Stony Brook University and Brookhaven National Laboratory that covers approximately 140 kilometers, which would make this a very important next step in proving all of these ideas. But despite these experiments being really intriguing and showing us something that we didn't really know before, Dr. Hoda himself is not particularly impressed, mostly because it does involve pre-entangled particles and a system that's already pre-connected, with the entanglement itself specifically being created for various types of manipulation. But his goal is to try to see if we can actually harvest the zero-point energy. Can we somehow actually extract energy from the vacuum itself by injecting the energy from elsewhere and by somehow entangling all of this in the process? Something that currently nobody knows how to do. But just the fact that these experiments show that we can actually do this, at least on a much smaller scale, all of this could one day lead to some really important discoveries when it comes to things like the quantum internet. And so not just transferring information like it's done today in quantum computers, but also transferring tiny bits of energy. But there's still a really big question where all of this leads in the future. It's quite possible that all of this might have extremely limited application, and it's also quite possible that the quantum internet might never become a reality. Nevertheless, these experiments could definitely provide answers about the universe itself. And once again, many of these answers seem to actually guide us toward black holes. It does look like these unusual objects seem to hide quite a lot of answers to everything. But at least for now, two really important experiments showing us that things in the quantum world are definitely quite strange, and showing us that the negative energy might be possible after all. But we'll talk more about this once more experiments and more investigations are done, and once the scientists actually come up with something even more exciting. Hello wonderful person, this is Anton, and so today we're going to try to tackle the question of, do we live in a simulation? Is this world right here real, or is this just an imaginary world created by some kind of a supercomputer? And are we all just simulations inside the computer, living our lives, pretending that it's all real? And to be honest, we're not going to be able to answer this question in this video, but we are going to actually tackle something else. Is it even possible to answer this question? And that's, of course, to me, as a science communicator, a much more interesting perspective. Because there are scientists out there that are trying to devise different experiments in order to see if we are in a simulation after all. Although, spoiler alert, at the moment the answer does seem to be no. But let's talk a little bit more about this, and let's maybe start with a bit of a history, just to understand that this is a really ancient question. As a matter of fact, it was even asked by the ancient Greeks. The famous Plato had a few propositions on the human perception, and even implied that maybe we don't really see what we actually see. Maybe all we see are just shadows on a wall. But he was obviously not the only one. For example, various Chinese philosophers, such as the Chinese writer Zhuangzi, had a passage known as the butterfly dream. Just as the name implies, in the passage, someone dreams of being a butterfly, flying around, waking up and realizing all of it was just a dream, even though it looked and felt so real. But this was really common amongst the Greeks. Monimus talked about it, Anazarchus talked about it, and it was brought up over and over again and became a pretty popular topic in philosophy. Even various Mesopotamic cultures, such as the Aztecs, had a few stories where the world was imagined to be nothing but a painting created by a god, with each of us just being the characters in his painting. And so when it comes to philosophy or philosophical concepts, this is definitely a really big one and quite popular throughout the ages amongst various cultures. But naturally it's become a little bit more popular in modern days, and there is a really good reason for that: video games. But I guess also things like virtual reality, the idea of metaverse, and so on. Here, we now actually have physical examples where you can become someone else. And sometimes it does start to feel quite real. Since the computers have been getting more and more complex over time, and since we reached the point where we can even simulate time itself by simulating the galaxy creation, star formation, and the creation of matter over billions of years, it's sort of natural to assume that at some point the complexity is going to become so ridiculous that none of this will be different from the actual reality. Although here, a really important correction. This is just an assumption. At the moment, all of these supercomputer simulations are still relatively primitive. For example, the size of a single particle here is usually in hundreds of kilometers. Obviously not a tiny particle like in the real world. But despite of all of this, it still is logical to assume that, well, maybe there is something to this idea. As a matter of fact, quite a lot of thinkers, quite a lot of scientists have been thinking about this and have been actually arguing about this to some extent. I mean, obviously Elon Musk brought up this idea a few times, but so did Neil deGrasse Tyson, with him thinking that it's a maybe 50-50. But this is of course all philosophy. And since this is not a channel on Asian philosophy, nor is this a channel that tries to speculate about things too much, I wanted to actually talk about the science, or is it even possible for us to prove any of this? Because what makes it scientific is of course the fact that it can be proven, or more importantly, disproven. There is some kind of an experimental setup. And if it's just an idea that can only be thought about and not tested in any way, well, in that case, for me personally, it doesn't really matter that much. I'm not particularly interested in untestable ideas. So, science. Can we actually do it? With the answer being, maybe. But in order to even understand how this could work, we first have to understand these scientific concepts that would apply to this simulation hypothesis. Although first, a quick clarification. This is not to be confused with the holographic principle. The principle from the string theory. And I know that some people have confused these ideas because I've got so many emails about this. The holographic principle simply states that, according to string theory, the world we live in, the three-dimensional, or I guess four-dimensional world, is actually created by extremely minute particles as they sort of project the entire reality on a much bigger scale. And so here, it's still a real world, but it's just created by very minute, tiny strings that then form the reality around us. Here, nothing suggests that this is a simulation at all. In contrast, the simulation hypothesis is basically the premise of the movie Matrix. So just a bit of a clarification here. And so the question is, what exactly are some of the scientific signs potentially pointing at this being true? Well, the first one is based on what we know about video games and virtual reality. All computers today obviously have some kind of a processing limit. For example, I myself could not even use virtual reality sets up until extremely recently. Some of the older virtual reality sets were just a little bit too slow and would give me and a lot of other people a feeling of dizziness, even if using this for just a few minutes. Now the speed is much faster, so it is a little bit more comfortable to use, but still not perfect. And so in this sense, there is a kind of a limitation based on the processing power, usually from the graphics card or the computer itself. Likewise, there is something very similar right here in the universe we live in. The limitations posed by the speed of light. And it just so happens that, according to Einstein's theories, once you start moving fast enough, the universe reacts accordingly, slowing down everything around you. In other words, one way to explain time dilation is by actually invoking the idea of simulation hypothesis. But this is still a little bit too philosophical. There's no actual proof just yet. Yet it's still unexplainable by the physics of the universe itself, and is definitely some kind of a limitation, physical limitation, in the fabric of the universe. Or the graphics card of the universe just has a certain limit. But still untestable, still no way to scientifically prove or disprove this, which puts it more in a philosophical basket, not in a scientific basket. We need something different. And so if we make an assumption that the simulation we live in has limited resources, and it cannot simulate everything in the universe all at once, there's maybe something else we can try to focus on. The idea is coming from quantum physics. If this is real, so basically if we do live in some kind of a video game, just like the video game, to save on processing power, the universe might only create the worlds observable by other players. Or to rephrase this, the world is only created when someone is looking at it directly. Everything outside of this world does not exist until observed. And this idea of the observer is very reminiscent of main ideas in quantum physics. We know that the observer effect plays a huge role based on various experiments, such as the famous double slit experiment. The experiment that has proved over and over again that on a quantum level, things can act both like a particle and a wave, and even large objects can exhibit wave-like properties, creating an interference pattern that disappears completely once you start observing the particles passing through the double slit. And so just like in video games, for some reason in a lot of quantum physics experiments, it's as if the world is rendered only when observed. And it's actually at this point where we kind of cross the boundary between this being a philosophy and potentially a scientific experiment. There's maybe a way to test this and to see if it's actually true. So how exactly do we test if this system only calculates reality when information needs to be processed for some kind of an observer? Or how do we test if the world does not exist when no one is looking? Well, in this case, this would also involve some kind of a double slit experiment, but this time with a bit of a twist. Or an additional layer involving even more uncertainty of whether there was an observer to begin with. And so in the regular version of the double slit experiment, when you fire single photons at a double slit inside the screen, you're going to start seeing this unusual pattern that's usually expected when the photons start acting as waves. But by adding a detector that's able to check which slit was used for the photon or the electron to pass through, this actually changes the pattern that's produced. It then starts to appear as if all of this was particles. And that's of course the main discovery from back in the days. Photons can be both particles and waves, but they cannot be both when observed at the same time. So it's a kind of a paradox here. A paradox that can to some extent be extended even further if you try to find a way to even make the observer itself kind of random and completely unpredictable. In one version of this experiment, the scientists proposed that maybe we can use various USB drives to collect the actual data that's not seen by anyone including the experimenter. And you actually keep doing this randomly until you collect enough of these flash drives to contain tons and tons of data that's not been seen by any physical observer, a human being. And because even the observer part is now randomized, even without looking at the data, you now randomly remove some of these USBs with, for example, a flip of a coin. And if there is a simulation, or basically if the test is successful, the scientists believe that the remaining data in these USB drives is going to start producing its own interference pattern corresponding to the randomness with which USB drives were destroyed or removed from the data. Or in other words, if the actual human observer did not matter here, the USB drives will create some kind of a random data indicative of a wave pattern extremely similar to the data produced by any experiment involving double slit. But if the observer did matter, the actual pattern will be a little bit different, possibly even very different, as if all of the collected data did not involve an observer, and so there's going to be some kind of a bias. And to some extent this might answer one question. Does the conscious observation of an experiment play a role in providing us with a collapsing wave function? Or can all of this be achieved by a simple physical apparatus, such as a computer collecting USB data? And so if the human observer does not matter, none of this will change at all, and all of this will provide exactly the same results. But if the observer is important, the results will be different. However, even though it sounds like a very simple experiment, even to date, since the original proposition in 2017, it has not been conducted successfully. It is still really challenging to set this up and to make it work in order to avoid any potential bias or any potential interference. And so the biggest challenge right now is to actually set up the experiment without any potential biases, without any potential interferences. Hasn't been done yet, but could be done once someone comes up with something really intriguing. And so it's still possible to make this very biased. But nevertheless, this is at least one potential way of testing this somewhat philosophical idea and to possibly give us a final answer. Do we live in a simulation after all? But here's the thing. There's at least one more experiment that's being planned by someone entirely different, using a slightly different method. And it's planned by the Information Physics Institute that I've briefly discussed in one of the previous videos, somewhere in the description. But we'll talk about this in the next part of this video. And so what's the answer right now? Well, the idea is still kind of philosophical, the premise is still kind of unproven or even without a potential proof, but based on our understanding of quantum physics, and based on what we know from various experiments such as the double slit experiment, there's maybe a way to prove or disprove this once and for all. Although I'm still going to err on the side of caution here and suggest that we probably do not live in a simulation. So yeah, go to work tomorrow, or to school, or just go and do your thing. Don't pretend that any of this is unreal. And here's actually another philosophical proposition that kind of bothers me with this. If we do live in a simulation, it means that that other world that we live in is not very good. Because think about it. Usually we play virtual reality games to escape the reality here. Escapism. Yeah, that's not a very happy thought. When I was originally planning this video, I didn't even know what to call it. My script for this video is actually called Bizarre Quantum Effects. And that's because it's essentially a collection of recent papers from the last few months describing absolutely mind-blowing effects related to quantum physics that essentially highlight how absolutely incomprehensible the universe actually is. And although in the human world, we're used to solid objects, things that sort of behave classically and move in a certain way, like this beautiful Churyumov-Gerasimenko comet, underneath all of this, there is quite a lot of quantum stuff going on that actually does affect us physically without us realizing or feeling it in any way. But the main reason we're talking about this today is because of this recent announcement and a recent study that essentially confirms a phenomenon that was kind of speculated about for several years. A phenomenon referred to as the quantum superchemistry. And so, hello wonderful person, this is Anton, and in this video we're going to discuss some of the major discoveries, but obviously not all of them, when it comes to quantum physics and quantum effects affecting real world around us. Or potential discoveries like this one right here that can actually change our understanding of how things work. And let's actually start with this study first. Many-body chemical reactions in a quantum degenerate gas, with the idea being really simple, trying to figure out if chemistry or chemical effects can be improved in some way by using quantum physics. Now this idea of quantum chemistry is far from being new. It's something that's pretty well understood and something that's been studied for a very long time, but what's different about this particular study is that it actually physically tries to test if certain atoms supercode to produce a quantum state could then also participate in chemistry as a single object. Or in other words, if we were to create what's known as the Bose-Einstein condensate, a pretty well understood concept which usually occurs when you have a bunch of atoms or a bunch of particles cooled down to behave as a collective quantum state, could then be turned into more complex molecules by interacting with similar quantum states of potentially other or maybe even similar atoms. And based on this particular study, the result seems to be yes. In this case, by taking atoms of cesium and making them ultra cold, they created a Bose-Einstein condensate that behaved as a single object. And one of the first observations here was actually a major decrease in particle collision, suggesting that each of the particles now behaved as a wave. So basically atoms here were no longer colliding. But even though the atoms were not bumping into each other, they were still forming new molecules, cesium molecules, and surprisingly were doing so extremely fast. But in order to start a chemical reaction, they essentially introduced magnetic field that would then force some of these atoms into molecules. Although all of this was happening much faster than in a classical reaction, essentially implying that in quantum world, even chemistry obeys different rules. And so even though the particles were not colliding, which is what's expected from a chemical reaction, they were forming new molecules extremely fast, which is now a direct confirmation of what's known as superchemistry. More specifically, quantum superchemistry. Something that was only proposed a few years ago, but something that's now been definitively proven. But obviously the next step here would be using much larger molecules in order to take this even further. Because this is the first such discovery, it's still unclear where all of this goes just yet. But even though this quantum reality might sound kind of far-fetched and potentially not really important, it's really the only reason we even exist. Because even on the fundamental level, for example, things like the sun are able to produce energy only because of quantum effects. So for example, hydrogen fusion that happens inside the sun is actually a quantum process and not really a classical process that we usually assume. And that's because most textbooks don't really explain what's happening here. The explanation usually involves two atoms of hydrogen turning into helium and converting some of the mass into pure energy. But the reality is that these atoms are super tiny, and even though they move really fast, and there are something like 10 to the power of 56 protons inside the sun's core, pretty much none of them have enough energy to suddenly fuse into helium. Or at least if you consider each of these atoms as a kind of a sphere or a kind of a particle moving at fast speeds colliding with one another. So technically, sun should not even shine. Yet we know it does, and we know exactly how much energy it produces. And that's because ultimately, each of those hydrogen atoms can also be described as a wave. And once you take the wave function into consideration, it all suddenly starts to make sense. And so instead of a particle, we have these tiny waves, once in a while touching tips, or essentially sort of going through one another. And occasionally, they merge, creating helium. The process itself is not very efficient and only happens sometimes, but this is the only way to explain how the sun is able to generate energy. It's a purely quantum process, and it's the process that drives the entire universe. But this is of course just one of many examples. And intriguingly, in 4.5 billion years of its existence, the Sun lost approximately a Saturn worth of mass through these unusual quantum effects. All of this naturally converted to pure energy. But there are some other quantum effects out there that have even more direct influence on everything around us, including ourselves. Here's the famous phenomenon known as quantum tunneling. This is of course a really old idea, it's nearly 1 century old by now, but it's been experimentally proven many times. Because of the particle-wave duality, when a certain particle hits a wall, some of the waves can actually tunnel through the wall and end up on the other side. But as strange as it sounds, it's one of the most unusual phenomena that's used in modern science to look at ridiculously small objects. There's a really cool microscope known as the scanning tunneling microscope that I've personally used myself to literally move atoms around. I actually wanted to make a video about this a few years ago, right before unfortunately COVID started, but it's a ridiculous concept that depends entirely on the idea of tunneling. Here we can see atoms individually through the tunneling effect produced by moving a tiny needle right next to each of the atoms. And it's something that's actively used today in a lot of different facilities around the world, trying to conduct some of the most complex research involving atoms. Now, hopefully one day I'll get to make that video about that particular research, but in a nutshell, it's just a mind-blowing concept. Atoms, or really anything, can technically tunnel through walls or even empty space and end up in a different location. Now, why exactly does this matter? I mean, obviously most of us are probably not going to be using these microscopes anytime soon. Well, it's actually because, once again, of chemistry. And here's another study you can find in the description that finally proves tunneling does actually cause chemical reactions. In this case, this was a reaction between hydrogen and deuterium ions, where a molecule of hydrogen collides with deuterium, producing a very specific ion. But in this case, it's the quantum tunneling that causes the formation of the ion. Except that this reaction is once again somewhat slow. It actually took approximately 15 years to finally physically prove it and to accurately measure everything. Here, this tunneling only occurs in about 100 billion collisions between hydrogen and deuterium. Once again, doesn't happen very often, but does happen enough to cause a change. And here we come to the most important discovery from the last few years. This also affects our bodies. It affects our DNA. There is now proof that quantum tunneling actually causes mutation inside our bodies, and there's pretty much nothing we can do about it. And so in this particular study, researchers discovered that sometimes hydrogen atoms inside DNA can actually jump from one side to the other, causing certain DNA molecules to change, literally causing a non-standard form of DNA-based mutation. Now, this is once again super rare, and the body is usually able to repair DNA molecules that are indifferent, but because of the sheer amount of DNA molecules in our bodies, sometimes this does happen and the molecules spontaneously change through the process of quantum tunneling, with the scientists in this paper even suggesting that this is probably an extremely potent mutation process, very likely affecting a lot of biological organisms, especially the ones that are more complex and that generally live much longer, kind of like us. And intriguingly, it's really the warmth inside the cells that seems to activate protons to sometimes create this tunneling jump. And so basically, just by itself, the mutation seems to occur naturally without anyone doing anything. Which is actually kind of mind-blowing. It means that mutation occurs without anything. Even if you place the organism completely isolated in the middle of nowhere, it will still mutate with time just because of these unusual phenomena. And I really shouldn't be saying organism because it basically affects you and I as well. And all of this is just a natural component of the universe. Strange quantum effects that are all over the place, but that we're mostly discovering because of these new brilliant studies. And so even though we see the classical world around us, underneath this classical world, it's the quantum reality that pretty much controls everything. Hello wonderful person, this is Anton, and today we're going to be discussing the movie behind me. Okay, technically not the movie, the science in the movie behind me. The movie that just won the Best Picture at the 2023 Oscars. And the movie that if you haven't seen yet, you should probably watch. It's probably one of the best movies I've seen in a long time. With a lot of quirks, a lot of humor, but most importantly, quite a lot of really intriguing scientific concepts. The concepts that we've discussed previously in some of the videos in the description, but also the same concepts that resulted in the Physics Nobel Prize in 2022. The now proven ideas behind quantum physics, and the experiments that solidified that quantum physics is an actual phenomenon that involves several major concepts, including things like superposition and entanglement. But by extension, to try to explain some of these concepts, it led to further propositions involving the idea of multiverse, one of several explanations trying to understand how and why all of this works. And so in this video, I wanted to basically answer two questions. The first question is in regards to the movie. And without spoiling anything about the movie, the question is really simple. How scientific is this? Does this actually make any sense? With the other really important question being, do we have any physical proof that any of this is real? Or specifically, that the multiverse actually exists? That there are multiple universes out there with maybe multiple copies of all of us? Something that does exist in comic books and of course this movie, but something that might not exist scientifically. So let's discuss this in more detail. And no, you definitely don't have to watch this movie in order to understand what we're going to be talking about. And really the only thing I'm going to mention about the movie is that it kind of involves the idea of parallel universes or the idea of multiverse. And from the quantum physics perspective, all of this relates to the concept of superposition. Or in other words, something can actually exist in several different states at the same time until that something is observed, at which point it collapses and assumes only one of the states. And this is of course where we have these famous experiments, such as the iconic double slit experiment, that essentially showed us that by observing something, it's possible to create completely different interference patterns. In essence, collapsing a variety of states into one single option. Or I guess the more famous example here is of course the iconic Schrödinger's cat. In this unusual thought experiment, Schrödinger actually argued for the absurdity of this particular idea. He suggested that if the cat is inside the box and there's some kind of a poison in there, it's impossible for the cat to be both alive and dead at the same time. In other words, he suggested that the ideas in quantum physics might have some other explanation. Yet today we know that, despite this sounding kind of strange, for particles or objects obeying quantum physics, their properties do indeed assume superposition. They can have several properties all at once until an observation is made. At which point we refer to this as a collapse. They assume the property and become a classical particle. Although intriguingly enough, as I'm going to be discussing in another video, this property or these quantum properties technically can be applied to much larger objects, including objects that are much larger in size, possibly even a cat. Although in this case, I don't think the cat would survive these particular procedures, mostly because the conditions here have to be extremely cold, pretty much almost at the absolute zero. But all of the experiments in the last few decades pretty much prove this more or less correct. As in, they prove the ideas of superposition and entanglement, the principles from quantum physics. But even though these principles make sense mathematically and could also be applied to make a quantum computer, it's still not entirely clear what's the actual bigger picture here. Does any of this math actually imply that there are these multiple universes, or that we have these parallel universes existing simultaneously until something collapses them, determining an actual outcome? Well, here's what we know so far, and it's actually not that much. First of all, this is obviously not a new idea. The quantum physics explanation is relatively new, but the idea of having multiple Earths, or universes that restart over and over, is actually thousands of years old and was even proposed by ancient Greeks. But it wasn't until the 19th century debates that some of these ideas started to be discussed more scientifically. And the concept of multiverse has at least three main explanations, all three coming from different branches of physics. One of them is from the string theory, which about 20 years ago tried to predict some of the observations from the universe, and as a result, the only explanation that made sense was the one where there were approximately 10 to the power of 500 universes in existence. Although today this particular explanation and the string theory itself is not actually as popular anymore, because a lot of other observations from around the universe in the last 20 years simply could no longer be explained by the string theory, which instead of making string theory a solution to everything, created a lot more problems. The second pretty well-known explanations for the multiverse comes from the physics of inflation, the concept that tries to explain how certain things in the universe manage to become so far away from one another. And the explanation here suggests that in the first fraction of a second when the universe just began, for some reason it suddenly expanded, increasing in size by a huge number, something like 10 to the power of 60. It's never really been explained why it did so, but the actual observations from around the universe, specifically from various really faraway objects, do actually hint on the universe suddenly expanding to extremely large volume in a very short period of time. And so this idea of inflation today is one of the major explanations for some of the observations. But in inflation cosmology, there is no specific explanation for why exactly our universe even began. And so it's possible that during this inflationary period, a tiny part of space-time has gone through the Big Bang and basically formed the universe that we know. But in this idea, along the space-time, it's possible to have these other bubbles of universes, or pocket universes, that might have experienced something similar, together forming some kind of a multi-universe. Although in this case, none of them are connected to one another, and even the closest one would be ridiculously far away. Although it's also been suggested that if one of them expands far enough and starts to affect the other one, we might be able to see certain signs by looking at some of the oldest light in the universe. So far, nothing like this has been seen. And then the third concept, and that's the one that's being dealt with in the movie, is the concept involving the collapse of the wave function. And this is based on the concepts proposed by Hugh Everett back in 1957. Back then he referred to this as many worlds interpretation. And he was the first to propose it, but unfortunately was not taken seriously by anyone, and ended up being extremely depressed because of this. So if only he could live until 2023, when the movie using his concepts actually ended up winning an Oscars. But in a nutshell, his ideas were really simple. Because there was no other way to explain what happens during the collapse of a wave function, he essentially assumed that when this measurement happens and when the wave function collapses, the universe literally splits in parallel versions, which then end up evolving on their own. And so for every single quantum particle that at some point ends up collapsing, you'll get a completely new universe. Definitely the most exciting and the most intriguing explanation of all provided so far. But also an explanation, just like the other ones, that unfortunately does not have any physical or scientific evidence. Or in other words, all of this is still very metaphysical, extremely philosophical, and makes a lot of fundamental problematic assumptions. For example, one major assumption here is that these waves are somehow real, that they somehow exist out there, and are possibly even real objects. But nothing in quantum physics states so. The actual explanations are all mathematical, and the math here only provides probability. It does not tell us that these are physical objects, and that these somehow exist out there in the universe. And there's definitely no proof or any observational data that any quantum physics concepts are physical in any way. In other words, the wave function is just that. It's a function. It's not a physical object that can be touched, that can be used, or that can collapse into something else. And so applying it to the rest of the universe might not be very scientific, especially because it cannot be proven or disproven. But more importantly, except for the few experiments that do involve wave functions, that do exhibit quantum effects on smaller scale, when it comes to seeing any other effects, such as the multiverse, there is absolutely no evidence anywhere. Even though there were suggestions of that evidence before. And here's probably one that kind of made rounds a few years ago, and I believe I've discussed it on a channel as well. This was in regards to the observations of one phenomenon in outer space known as the cold spot, an unusually large imprint visible in a cosmic microwave background that appeared somewhat unusual when it was originally discovered. And approximately 5 to 6 years ago, someone actually tried to propose this as an explanation for potential evidence for maybe multiverse. Essentially, another universe out there pushing on the universe that we live in, most likely as a result of expansion, with the interaction between these two universes resulting in an unusually cold spot visible in the CMB. And so this right here provided this unusual evidence. The only piece of evidence ever for maybe the existence of another universe somewhere out there. But here's the thing, this was very controversial back then, and it's actually still very controversial, and not a lot of scientists agreed with this, for a very simple reason. There was a much better explanation involving what we know about the universe already. This was probably a location of a very large supervoid. It's known as Eridanus supervoid, and we've discussed this in one of the videos in the description. A supervoid would explain this much better, would not involve any multiverses, and actual physical evidence for the existence of this supervoid was later discovered using some of the more advanced observations. So unfortunately, this was not the evidence for the multiverse either. Today it's believed that the original proposition was only made because the early observations were not as detailed as the ones created by the Planck telescope years later. And so, unfortunately, no physical observation. So does that mean that multiverse probably does not exist? Well, there is another explanation. And it's not really observational or physical, it's more or less statistical. And it's something that we actually cannot explain today. And here the idea is once again kind of simple to understand. Our universe seems to contain a lot of physical constants. And some of these constants, like for example the fine structure constant, have to be extremely precise for things to work the way they work in the entire universe. Changing just a tiny number inside these constants would actually shut down everything. For example, for the fine structure constant, a small change would result in no nuclear fusion, no stars, no supernova, and no elements created anywhere. Yet somehow all of these constants are perfectly calibrated, with a lot of other physical ideas in the universe creating just the perfect condition for things like stars, planets, and of course us to form. And so the statistical explanation for the multiverse would be, well, it's quite possible that there are indeed infinite number of a lot of other universes where the constants are different. And in those universes, things just didn't really work out well. Yet here we are living in the perfect universe with just the right constants and just the right mixture of everything else and of course other physical laws that allowed for life to form and allowed the intelligence to form to then contemplate and discover all of these unusual effects. But once again, not a particularly satisfactory explanation, and not an explanation that we can either prove or disprove once again. And that's unfortunate, because it just means that the multiverse as a concept is still very, very metaphysical and not scientific at all. There's really no way to find any evidence or to prove this, at least based on any modern observations. And the idea of collapse coming from the quantum physics does not actually provide any way for us to understand what goes on with various particles right before they collapse or as they maintain their wave function. But chances are some of the answers might be provided in the future as the scientists conduct more experiments using very large objects that actually can become quantum in some way, and we'll discuss some of this in another video that's going to be on the channel really soon. So do check out the link in the description that might have that video there already. And so, well, to summarize, great movie, definitely deserving of the Oscars, and it's definitely one of those movies I'll be coming back and watching over and over because it was just kind of fun. But scientifically speaking, it is based on a somewhat metaphysical interpretation of the idea of superposition and the collapse of the wave function. We actually have no idea if the multiverse is a real thing and if there are other yous and me's out there. But honestly, for me personally, someone who's not particularly religious, even though I tried a long time ago, and for someone that's experienced quite a lot of unfortunate tragedy in my life in the last decade, this interpretation is the one that makes sense. Because I truly want to believe that somewhere out there, somewhere in another universe, both my mom and my youngest son Neil are still alive, still chilling, playing together, doing all kinds of grandma and son things, and we're all kind of happy. And so I guess it's more of a faith thing. And it's also kind of a way for me to cope with a lot of this without having an actual religion. But other than that, that's unfortunately all we know. And by the way, if like me you're obsessed with these concepts, and if you've also enjoyed the movie that I mentioned, you absolutely have to check out this TV show as well. This is by far one of the most mind-blowing and one of the most interesting TV shows I've seen on the quantum ideas pretty much ever. Definitely worth your time and will definitely make you question your reality.